maximally y. Because the correspondence between irreducible components of x and y, and so obviously closed irreducible subsets of x and y obtained by taking the closure of the image just corresponds, and we identify closed irreducible subsets to their generic points. I mean, there's a one-to-one correspondence, just corresponds to the map F itself. And then our statement here just means that if we have a maximal point in x which just cedes, it means that we are taking an irreducible component. This goes into a maximal point of y. Now, why is this? Well, it comes from the fact that a morphism at x be a maximal point, and that y be a point, the point below. I assume, let's prove that y is maximal. We know, so we have to prove that every generalization y prime of y is equal to y. But because the morphism is generalizing, you see, a generalization of y prime comes from a generalization of x. And x prime is equal to y, therefore y prime is equal to y. So this property I've just stated, that maximal points go to maximal points, is a consequence of the morphism F being generalizing. Of course, as flatness and, in fact, also the property of being generalizing is stable under restricting to subschemes, let's say. That's because flatness is stable on an arbitrary basic function. Being generalizing is anyhow stable under these special types of basic extensions, taking inversions, that's pretty clear. We see that in such a situation, after we make such a base chain, after we restrict to what lies over the subscheme y prime of y, closed for instance subscheme which we refer, then every irreducible component of x prime again dominates an irreducible component of y prime. So this is true whenever we have flat morphism, and more generally whenever we have a generalizing morphism. And in fact, it's pretty easy to see that the morphism is generalizing if and only if, for every closed subset of y, and we can even say for every closed irreducible subset of y, every closed irreducible subset of x prime dominates a closed irreducible subset of y prime. So we have used this fact, I think, once or twice in the course about algebraic groups. In the following situation, we have a field extension k prime over k. We have a scheme x over k. We make the field extension, the extension of the ground field. For the scheme, we get a scheme xk prime lying over x. Then every irreducible component of xk prime dominates an irreducible component of x. Because k prime being flat over k, xk prime is flat over x. And we just use the previous statement. So you see all this kind of goes along with the intuition that flat morphisms are morphisms which are kind of, wherever they're not empty, I mean, that are kind of spreading out x over y, you see. It's the opposite of a flat morphism would be, for instance, an immersion of a subvariety, like a point in a line, you see. Then the subvariety is not of the same dimension. And there's the irreducible component. Let's look at this morphism, you see. Here the irreducible component is just the point itself, let's say. It goes to just a point which is not an irreducible component. If you figure out a flat morphism, you see, you would rather see lines that are kind of horizontal and that cover this line. There should be no component that is like this, and that would be mapped just to a point. That's the situation. Now, let's go back to.
Excuse me.
Yes.
Is there is there a nice class of morphisms for which you can give a completely topological characterization of flatness?
Of flatness? Yes. Let me give you a sermon to this effect. There are various situations where, how should I say? Yeah. So let me give a few examples. Now a little less formal, let's say. Let Y be a regular scheme, in a certain scheme, let's say, of dimension 1. So let's say a non-singular curve, something like this, or the spectrum of the integers, the spectrum of a Dedekind ring, for instance, of a unit, how do you call it, of a principal ideal domain, such a thing. So the local rings of this will be just these evaluation rings. And now we use the fact that, and the affine rings of Y will be in fact Dedekind rings. And we use the fact that the module over a Dedekind ring, so for instance a module over a principal ideal domain, is flat if and only if it's torsion free. Let's perhaps develop this example. If A is an integral domain, modularly, so that the notion of torsion-free modules makes a sense, then if M is flat over A, then M is torsion-free. What does that mean, torsion-free? That means that if F is an element of A that is different from 0, then the multiplication by F and M is injective. That's what it means. The torsion elements are exactly those that are killed when multiplied by an element different from 0. And we want that there are no torsion elements except 0. Now, we will have to prove that this is injective. But this is deduced from the multiplication by F and A by just tensoring with M, and because A is an integral domain and F not 0, the homogeneity by F and A is injective. Therefore, it's injective in M too. So, flat modules, you should view them as being without torsion, whenever this makes a sense. But there's a converse if A is a Dedekind ring, or what amounts almost to the same, at least when we localize it amounts to the same in the principal ideal domain. So then, because flatness is a purely local domain, so you can even reduce to discrete vibration rings. Why is this? Should I prove it? Because let's prove it after all. So we are reduced to the case when we are over a discrete vibration ring, which is a unique factorial, which is a principal ideal domain. And now a module, flat module, M being without torsion, we have to prove that M is flat. But M is the Dirac sum, the Dirac limit of the submodules Mi that are finite type. And it's pretty clear that a Dirac limit, filtering Dirac limit of flat modules, is flat. Because a Dirac limit tensoring with the module N would be the Dirac limit of tensoring with the modulus Mi, and the Dirac limit of exact functors is exact. So we have only to prove that the Mi's are flat and they are of course torsion free, because a submodule of a torsion free module. So we are reduced to the case when M itself is a finite type. But then a module of finite type, which is torsion free over an unique factor principal ideal domain, is free, and therefore it's flat. Free module, of course, is flat with Dirac sum of flat modules in the ring A itself. All right. So therefore, flatness over a curve, you see a non-singular curve, is something which is a pretty coarse property. Now assume that we have a scheme X over Y, and assume for simplicity that X is reduced. I don't want to have any trouble with embedded prime or such things. Then x is flat over y, if and only if every component of x dominates y. That's an easy consequence of what I have said so far. Then x flat, if and only if every component, irreducible component of x dominates y, assume y irreducible, otherwise one should say dominates an irreducible component of y. We know, of course, that this condition is necessary for flatness, but it turns out to be sufficient, provided x is reduced. If x is not reduced, then the less than sufficient condition is that every associated cycle, but whoever knows what it means. So there may be no that just irreducible components dominates y. There should be no associated cycle, you see. That should be vertical. There should be not a string, you see, just of written input elements concentrated on a vertical. So this is a quite elementary case where flatness is very easily explained. So here it just means, that you don't have, let's say, in the case x reduced, that you don't have components that are vertical. That all components lie kind of horizontally over. Of course, some components may be of higher dimension. Now, there are some simpler cases. Assume that y is regular, but not necessarily of dimension 1. And assume that x is of finite type over y, or locally finite type, and that x is Cohen-Macaulay. Now, this is a slightly technical notion, so if it's too technical for you, just replace it by x being irregular. So x and y both know similar schemes, you see, and x of finite type over y. You really need this. Yeah, we better assume this. F of finite type, or local of finite type. In this case, f is flat if and only if for every irreducible component of x, all fibers have the same dimension, you see, so that you have a certain regularity. What shouldn't happen, you see, is that there are some fibers which are of a certain dimension, let's say dimension 0, and all of a sudden, you see you have a jump upwards at some special points, like if you blow up in something in some way. So then, under these conditions, f is flat if and only if. Assume x and y connected if you want. That means irreducible because they're regular. Then f is flat if and only if. And should be all components of all fibers have same dimension. It's not enough to say that all fibers should have the same dimension, say, all components of all fibers. Otherwise, what you would take is, you see, isomorphism like this. You see on one end an isomorphism, the identity, and then you take an isolated point and you add it to this. And now the fibers, of course, have all dimension 0. But this piece here, you see, how should I say? Well, there's something, but this was disconnected. No, it wouldn't work. No, in fact, no. In this case, maybe. Let's see. Can there be anything bad happening? No, in fact, it's enough. No. All components. You can state it either way. So it's as sufficient that all fibers should have same dimension, or that all components of all fibers should have same dimension. I assumed x and y connected here. That was it. So, and there are some. So this is. Well, you see, it involves some dimension theory, and we haven't done any dimension theory here. That's not, otherwise it's not too subtle, in fact. Flatness implies, you see, a certain continuity for the dimension of the fibers, precisely. It implies that there's no such a phenomenon as blowing up something into a fiber of larger dimension at special points. And it turns out that the converse holds true when we make strong local assumption x and y, separately like regularity. And then there's something pretty much subtler now than even this here, which is in the case when y is normal, f of locally or finite negation, and then you see if f is universally open, plus the fact that the fibers are separable. So I don't want any important elements in the fibers. This may give trouble. That this implies that f is flat. Yeah. But that's kind of deep. I mean, well, I mean, it's relatively hard techniques of local techniques of schemes. So here again, you see the assumption is of topological nature, f is universally open. Well, it's not topological in the strictest sense. I mean, it's not just a property of the map of topological spaces. It has to be universal. And the fibers should be separable, so I mean there should be no double fibers in such dirt. So it makes a good geometric sense too. And this would imply that it is flat. So I guess it's somewhere one of the various paragraphs of EJ chapter 4. So, are these examples satisfactory?
In the first example you gave, you said y regular.
Yes.
And then Euclidean scheme of dimension 1.
Yes.
What did you say about it? Because I got lost in the idea.
I said that a scheme x over y is flat over y. Assume the scheme already, if you have a reduced scheme over y, is flat over y if and only if each irreducible component of x dominates an irreducible component of y. If and only if, yes. And this comes as an easy consequence of the fact, you just look and you see as a consequence of the fact that a module over a discrete variation ring, let's say, is flat if and only if it's torsion free. You see the components that would not dominate a component of y, that would correspond to torsion modules. If you look at, let's see, in an affine case, let's say, if you look at the affine algebra of such a component, would be a pure torsion module. And that's the idea. But I mean, I could write it down in 5 minutes, I guess, or less. But maybe it's not worth it. Why don't you look through things as homework? Now let's come back a little bit to full faithfulness, to faithful flatness. Let f be faithfully flat. And look at the map which associates to every subscheme y prime of y the inverse image of this, which is a subscheme of x. So if the set of subschemes of y is called something like SS y, and the set of subschemes of x is called SSX, you have a map like this, and the assertion is that this is injective. this goes quite well with the Euler faithful flatness, meaning that you know what has been going on Y when you know what has been going on the inverse image. Alright, why is this? Of course, as the map is surjective, Y prime is known as a subset of Y, then we know it's the inverse image. So let's assume that we have two subschemes of Y, let's say Y prime and Y second, such that the inverse images are the same. So we know already that Y prime and Y second coincide as subsets. And therefore, replacing Y by an open subset in which Y prime equals Y second are closed, we can assume that they are closed subsets of Y. Of course, the flatness is conserved when I reduce the situation over this open subset. So we may as well assume that they're both closed in Y. And now they correspond to subschemes, basically subschemes of ideas J and J prime and OY. And to say that Y prime is J prime and J second, let's say, to say that Y prime is equal to Y second just means that these two subschemes are equal. But as a functor inverse image of modules is exact and faithful, two sub-objects of an object downstairs of a module that become equal after we lift must have been equal before. Alright, and now let's give a corollary. Assume that that we have a base change which is faithfully flat. S prime goes to S, and we're interested in morphisms between S schemes X and Y. And I claim that from over Sxy mapped into Hom over S prime, X prime, Y prime is injective. In other words, I claim that the functor in the inverse image functor going from schemes over S to schemes over S prime is faithful. Of course, this wouldn't be true if F was only flat, if it wasn't surjective, because then, for instance, the inverse image of a point that doesn't lie in the image would be the empty scheme, whereas it is not empty itself. You see, it is not isomorphic empty scheme, but its inverse image is isomorphic. Let's say we would have that. Let's say that if S is this point, there would be no homomorphism from S into the empty scheme. Also, over S prime there is. No, that's not the way of putting it. Well, why not true? Yeah. Yes. If S is a point of capital S that didn't belong to the image, assume that F is not surjective. Then we can find schemes lying over kappa S, lying over this point S, and two different morphisms between them, of course. That's pretty easy over any round we can find two schemes and two different morphisms, one to the other. But the inverse image of these two morphisms would be the same, because X and Y both become empty for S prime. So certainly, statements as the one as I'm giving now, it's quite essential that the morphism F should be fully faithful. F would be faithfully flat. Alright, now let's prove the statement. Now let's introduce the product X times Sy here. And we have this situation deduced from the situation there by base change. Call this product Z. So Z prime is a product of X prime and Y prime over S prime. Alright? And now let's notice that morphisms from X into Y over S correspond just to sections of Z over X. And such sections, they correspond to subschemes, exactly to those subschemes of Z such as the projection from the subscheme to X is an isomorphism. So the set of homomorphisms here can be viewed as being contained in the set of subschemes of Z. Those subschemes for which the first projection on X is an isomorphism. And the same here with the prime. And the map here, of course, forming graphs of morphism is compatible with space change. So this map is induced by the map here. But if S prime goes to S is faithfully flat, therefore Z prime goes to Z is faithfully flat too. And therefore this map is injected. And therefore the induced map is injected. Of course, the next step would be to determine which are the homomorphisms from X prime and to Y prime that come from homomorphisms of X and to Y. So this would already, we would say those which are compatible with the descent data that we have on X prime and Y prime. And after this, the step after this, which is a lot subtler, is to see which are the extra conditions on a scheme X prime over S prime which allow to reconstruct the scheme X over S from which it comes, and we'll find in certain cases we make certain assumptions. These are so-called descent data from X prime to S. So this we will deal with next week, I think. Maybe I can, however, so I can, I think we have no time to go into this today. But let me still state one important property about flat base changes that need not be faithfully flat that we are going to use. Let X goes to Y be a coherent morphism, which we will use this, among others, this assumption in order to deduce that for every phase equivalent sheaf F on X, the Dirac image is quasi-coherent. We have shown this. And now, let's make a base change. Y prime goes to Y, which is flat. And let's look at the situation reduced by base change. We have an X prime or Y prime with an F prime here. And here we have the sheaf F prime, which is the inverse image of the sheaf F, which is quasi-coherent. And let's look at the Dirac image of F prime. Now, without any flatness assumption, in fact, we do have a canonical homomorphism which goes from the inverse image of F star F into the Dirac image of F prime. So from F star F prime, so to say, which is the inverse image of this Y prime, to this Dirac image. Here's a pretty canonical map. Maybe I should define it so it's not too familiar. To give a map of this into a Dirac image is the same thing. You see, call this morphism called G, let's say. And the morphism up here, call this H if you want. You may use it. So this here is just G upper star of F, lower star of F. And we want to map it into the Dirac image of F prime. And that's the same thing as to map the inverse image of this sheaf by F prime of this sheaf here on X prime into F prime by the junction. But what is this inverse image here? We have a sheaf on Y, F star F. We take its inverse image by G first, and then by F prime. But that's the same thing as we took the inverse image here and then there, because the square is commutative. So that way you read the commutativity of the square. And therefore, this here is H upper star of F upper star of F star F. right? Did I get it? And this I should map into f prime. Yes, because we have a morphism which goes, a canonical morphism, which by adjunction, which goes from f upper star, from f lower star of f into f. Don't we? And therefore, if we apply h star to this, we have a homomorphism which goes from h star of this sheaf into h star f, which is f prime. Alright, so I had an intrinsic calculation of this arrow. We could also do it the other way around. Here I have used the fact that we are mapping a sheaf into a direct image. I could have used also the fact that we have an inverse image of something to another sheaf and use the junction formula the other way around. I would have gotten another description of canonical mapping. It turns out that the two are the same. Alright, and now the statement I want to make is that this canonical morphism is an isomorphism whenever the base changes flat. So it exists, of course, this canonical morphism without any assumption whatever on our morphism. In fact, it exists whenever we have a commutative square of topological spaces, of ring topological spaces. But in the situation we have here with f coherent and g flat and everything being schemes, of course, and the diagram being Cartesian, we have that this canonical morphism which goes therefore, I recall, from the inverse image of f star f into the direct image by f prime of f prime, that this is an isomorphism. So taking direct images commutes with flat base change, provided the morphism f that we are taking direct images with is coherent, and provided the schemes, the sheaves we are working upstairs with are quasi-coherent. The same, by the way, would be true if we take higher direct images. If we take Ri f star s, then proceeding much the same way as we had, we see that its inverse image on y prime is mapped to Ri f prime star f prime. It turns out that these are isomorphisms. So these kind of things are important consequence of flatness. I think it's a little late, so I will not give the proof, which is pretty standard. I mean, it's essentially the same kind of proof which I gave for proving that the direct image is quasi-coherent. Will kind of unsmooth the situation into affines. You have to do it in two steps, however, in order to take into account the fact that the intersection of two affines and x may not be affine. This thing is local on x and y. So eventually, everything boils down to the affine case, and we will see what it means then. Here, then we have a Cartesian square of rings, A, B, A prime, B prime. The arrows go the opposite way, of course. We have a module M over B, and you will see what our various operations are. Taking the direct image just means of restricting the scalars from M to A. And then taking the inverse image means that I take M tensor A prime. That's for one thing. And the other is making the inverse image here, that is cancelling over B with B prime, and then restricting the scalars to A prime. And I claim that the two are the same. Under the condition that A prime is flat over A. So what does this mean? It means that cancelling M over A with A prime is the same thing as cancelling M over B with B prime. Alright, why don't we leave this to the meditation? So that's what it really boils down to. And it should imply flatness of A prime over A. Using flatness of A prime over A. we have well under base extension and composition as it should. Now, it also started that's what other important things, properties have we seen. If A and B are local rings and A goes to B as a local homomorphism, then B is flat over A if and only if B is faithfully flat over A. In other words, if and only if spectrum of B goes surjectively onto the spectrum of A. And as a consequence, you have seen that if F is a flat morphism of schemes, and if you look at the induced morphism for the localized schemes, like this, for X point here upstairs and Y the point below, then these induced morphisms are always surjective. We say also that this is expressed by saying that flat morphisms are generalizing. And of course, as flatness is conserved by base change, this means that flat morphisms are universally generalizing. And as a consequence, something more or less equivalent to this property is the fact that every irreducible component of X dominates an irreducible component of Y. In fact, to say that morphism is generalizing means also that every irreducible component of X dominates an irreducible component of Y, and the same property is conserved by replacing Y by any closed subscheme or closed irreducible subscheme and looking at the inverse image. So in fact, the essential properties of the morphism between the localized schemes being surjective, and the fact that every component of X dominates an irreducible component of Y, this is just essentially the same story. So no vertical components in X over Y if X is flat over Y. Remember. Also, as a consequence of flatness, we have faithful flatness. We have seen that X goes to Y is faithfully flat. Then the map which goes from subschemes of Y to subschemes of X by associating to every subscheme of Y its inverse image, this map is rejected. So this is the very beginning of the story, which says that if F goes to Y is faithfully flat, then whatever, when we have something over Y, and if we want to know if something is true over Y, if it becomes true after making the base change, it was true before. For instance, if you have two subscripts of Y, you want to know if they are equal, and they become equal over X, they are equal before. And now the lecture of today will give a host of statements of this type. Before diving into this, I want to recall also another statement that we gave for flat base extension. If we have a flat base extension, it need not be faithfully flat, then this has a tendency to commute with direct images of crazy coherent sheaves and other. So to be specific, assume that F is a morphism which is coherent, that means crazy compact and crazy separated, and that F is a crazy coherent sheaf on X. Look at its inverse image on X prime, which is a crazy coherent sheaf on X prime. Here we have the morphism deduced by base change F prime. Then the statement is that the natural morphism which goes from the inverse image of the direct image of F to the direct image of the inverse image, here is this morphism, is an isomorphism. And the flatness of S prime goes into S is used in order to reduce to the case of X and S prime being affine. In fact, S and S prime being affine, this isomorphism is local both on S and S prime, so we can already assume S and S prime to be affine. But then we will decompose X into 5 number affine pieces and reduce the computation of the direct image to the computation of the direct images for the restrictions to these affine open pieces in terms of certain exact sequences, and we use flatness in order to ensure that exact sequences that are downstairs here remain exact after tensing. So that's essentially the story. And in the affine case, in fact, this is an isomorphism without flatness assumption. So let's say that this is an isomorphism if either the morphism of base change G is flat, or if the morphism F is affine. Assuming anyhow in the first case that F is at least that F is a coherent form. Because in the case when F is affine, then we can assume everything affine, and then the statement just boils down to the following. We have a ring A in algebra B over A. We make a ring extension from A to A prime. Alright, like this. We have a module M over B that corresponds to this sheaf F over X. We make the base extension to B prime, from B to B prime. This corresponds to taking the inverse image, and we restrict the scalars to A prime. That's the same thing as first restricting the scalars from A to M to A, and then making, so let's call it rather tensor product. So we make M tensor B prime. That's the same thing as first restricting the scalars to A and then making the Baker extension. We have this isomorphism, which is true contrary to what I stated, without any flatness assumption. A primes. It's a tautology essentially. Associative treatment of tensor products. Alright. And in fact, the same statement holds also for the higher direct images, if everyone needs them. So that's one of the many ways in which flatness enters technically in an important way into the formalism. Now we are going to descend by flat descent of all kind of properties. Let's give first the descent of some fineness properties. But for some of these descent, so the story is always the following. We have a morphism of base change. In most cases we will assume it faithfully flat, and we have something going on over S, and we want to see if something is true for this situation, and if it becomes true after base change, it was true before. And we are mainly concerned with the case when the something that we give over S is an S morphism of schemes. So we have two schemes X and Y over S, and we have an S morphism. So let's write it like this rather. And if you look at the call F, this S morphism, and if you look at the corresponding S prime morphism deduced by base change, and we want to prove that if something is true for F prime, it was true for F. And if the something is stable by base change, then we can say that it's true for F if and only if it's true for F prime. Alright, that's the general situation. Now we can also see that we can also view that X prime is deduced from X over Y by making the base change Y prime goes to Y. That comes from the transitivity of base change. And therefore, if S prime is, let's say, faithfully flat over S, then Y prime is faithfully flat over Y. And therefore, in these statements, we can always assume that S is equal to Y without, if it helps. That's no essential restriction. Now, let's give some statements now to this effect. So first about fineness properties and analogous things. So let's assume this. First, let's assume simply that G is surjective. Not necessarily flat. Then I claim that F is surjective if and only if F prime is surjective, and F is radicial if and only if F prime is radicial. We call it radicial means injective and remaining injective after any base change, or universal injective. Alright, so for surjectivity, note that if G is surjective, then what we deduce by base change G is surjective too. Of course, we know that surjectivity is stable on a base change, so we have to show that if f prime is surjective, then f is surjective. But if f prime is surjective, this compositum is surjective. Therefore, this compositum is surjective by force theory. This is surjective, so that's clear. On the other hand, f radical just means that delta f, the diagonal morphism corresponding to f, is radical. And of course, the same for f prime. F prime radical means that is surjective. To say that the morphism is radical means that the diagonal morphism associated to it is surjective, just like a map of sets is injective if and only if the diagonal morphism associated to this map of set is surjective. All right. And of course, delta f prime is deduced from delta f by making the same relation if s prime goes to s. And therefore, the case of radical is a particular case of the case of surjective. Now assume that G is surjective and quasi-compact. Again, we don't need that to assume that G is faithfully flat. By the way, in these descent theorems, sometimes if G, we have to assume not only that G is faithfully flat, but moreover quasi-compact. So don't be surprised if this enters here in the assumption. But flatness is not will not be needed either for the time being. Then let's see. Then F is quasi-compact, respectively quasi-separated, respectively coherent, let's say, if and only if F prime enjoys the same properties. So these are almost clear set theoretical and topological properties. Let's see. Of course, we know that quasi-compactness, quasi-separation, and coherence are stable under base change. So it's in this direction we have to prove things that F prime enjoys these properties. F enjoys them. So assume that F prime is quasi-compact. And let's prove that F is. So for this is purely local, so we can assume that y and y prime. Well, I mean, we can note that the assumption on G is satisfied also on y prime goes to y, so we can forget about s and s prime. So we can assume moreover that y and y prime are affine. And then to say that f respectively f prime are quasi-compact just means that x respectively x prime are quasi-compact in the absolute sense, quasi-compact topological spaces. On the other hand, this morphism being equivalence is valid whenever s prime goes to s is surjective only. Yeah. All right. Now quasi-separated is reduced to quasi-compact because it just means that the diagonal morphism is quasi-compact. So, and coherent is just the conjunction of quasi-compact and quasi-separated. What's this? I'm a little worried because there's something wrong. So assume I made some mistake in my argument. If f prime, I want to prove that if f prime is quasi-compact, then f is quasi-compact. I assume y and y prime. Oh, I see.
For the converse, you need.
Yes, I see. When I make the reduction, yes, I'm sorry. When I made the reduction to y prime affine, this wasn't correct. I wanted to prove because It's not sure that I can find an open subset here and an open subset there that's such as induced morphism is surjective. You see, the reduction to y affine is immediate, but the reduction to y prime affine is not so. So let's assume that, therefore, in our argument we can assume y affine. Then all we can say is that y prime is quasi compact. If we assume that the map is surjective and quasi compact, and we have to use it. Yeah. All right. And now, but that's enough in order to interpret the assumption that f prime is quasi compact by the fact that x prime is quasi compact. And if x prime is quasi compact, x prime goes to x being surjective. X is quasi compact. That means that f is quasi compact. All right. No. Otherwise, it would mean that for a morphism to be quasi compact, it's necessary and sufficient that the fibers are quasi compact. That's about true. Fine. Now, some fineness theorems where really flatness is used. Assume that G is faithfully flat and quasi-compact. So it's the assumption of our previous statement, except that we assume moreover flatness. Then I contend that f is locally of finite type, or locally of finite presentation, if and only if f prime is, and if we combine this statement with the previous one, we see that f is of finite type, which means just locally of finite type and quasi-compact, if and only if f prime is, and f is of finite presentation, which just means that it's locally of finite presentation and coherent has been dealt with here, if and only if f prime is. So we are reduced to look at these two local properties of being locally of finite type and locally of finite presentation. All right. Now, again, we may assume that s equals y, then looking at the situation up here. And the problem is clearly local on x and y, so we may assume as well y to be affine. Now, as the morphism is quasi-compact, y prime can be covered by a finite number of affine pieces. And so provided I replace y prime by y second, which is the disjoint sum of these affine pieces y prime I. All right, when I look at the compositum of y second lies over y prime, and if I view y second therefore of lying over y, then we see the following, that y second over y is also flat and surjective and quasi-compact because it's a compositum of two such morphisms. This is clear, because y second goes to y prime is quasi-compact, surjective, because y prime I cover y prime, it is flat, because opening crucials are flat. Alright? And on the other hand, if we assume that something is true for f prime, then a fortiori it is true after making the further base change to y second. It's true for f second. And therefore we are reduced to proving, if we want to prove that f then has the same property, we are reduced to proving it by replacing this situation by this situation. In other words, because we assumed G to be quasi-compact, not only faithfully flat, but also quasi-compact, we can reduce to the case when y prime in fact is affine also. Alright. Now on the other hand, being locally of finite presentation is something, or local of finite type is something which is local on x, and x prime, therefore, covering x by affine open sets, I can assume, and therefore x prime by the inverse images of these affine open sets, I'm reduced to the case when x is affine 2 and therefore x prime is affine 2. And now I'm reduced to a situation of pure commutative algebra, which is the following. I have an algebra V over A which corresponds to this situation. I have a base extension, ring extension from A to A prime, which is faithfully flat. I look at the algebra B prime over A prime, and I claim that B is of finite type respective of finite presentation over A, if and only if B prime is of finite type or finite presentation over A prime. So that's pure commutative algebra. I will prove it because it's so easy and so quick. We know that B is a direct limit of subalgebras of B that are of finite type over A, of course. And therefore B prime is the direct limit of the B prime i's, which can be viewed because A prime is flat over A, as subalgebras of B prime. Base extension passes through direct limits, filtering direct limits here. Alright? On the other hand, if B prime is of finite type over A prime, then one of the B prime i's must be equal to B prime for I big enough. Because if B prime is the direct limit of filtering system of subalgebras, if B prime is finitely generated, one of the subalgebras must be equal to B prime, it must contain the finite set of generators. Right, so B prime I is equal to B prime, and therefore, because A prime is faithfully flat over A, Bi must be equal to B. That means that B is finitely generated. Now, for finite presentation, we make the same thing. Assume that B prime over A prime is finitely presented. Let's assume the same. Let's prove the same for B over A. We know already that B is a finite type over A. Therefore, it's a quotient of a polynomial algebra C by some ideal J. And all we have to prove is that J is a finite type. Alright? What we know is that after making the base extension to the situation here, B prime is isomorphic to C prime over J prime, where C prime is a polynomial algebra over A prime, it's finitely number many generators, and that J prime is of finite type because B prime is finitely generated. So J prime is an ideal of finite type, that means as C prime module of finite type. So all we have to prove now is that if we have if as A prime is faithfully flat over A, of course C prime is faithfully flat over C. And all we have to prove is that if a module J over C is such that J prime is a finite type over C prime, then J is a finite type over C. That is, we have to descend now the property of being a finite type for modules. And that's the same story as before. We write J as the direct limit of submodules, of its submodules that are finite type. And we apply the same argument, this is clear. Now this argument here shows us that we can give a modular variant of this here. If we look at a quasi-covariant sheaf f on x and its inverse image f prime on x prime, then we can say that f is of finite type or of finite presentation if and only if its inverse image f prime is. Because here again we are reduced to the affine case, and the case of finite type we have just dealt with, and the case of finite presentation is reduced to this one by the same argument, knowing already that's a module. So the lemma would be the following: if A prime is faithfully flat over A, M and modulo over A, and if M prime over A prime is a finite presentation, then M is a finite presentation. We know already that M is a finite type. Therefore, a quotient of a free module of finite type by submodule R. We have to prove that R is a finite type. But M prime is isomorphic to L prime over R prime, L prime being free of finite type. M prime being of finite presentation, R prime is a finite type, and therefore R is a finite type. Alright, so these things descend quite nicely. So let's also remark, maybe we want to give the proof here, it's of the same kind, that f is locally free of finite type if and only if f prime is. And the same locally free of a given rank of finite type and of a given rank n, let's say, which corresponds to vector bundle of rank n, if and only if f prime is. For instance, a module f over x is invertible, which means locally free of rank 1 if and only if f prime of x prime is invertible. Here the essential thing was, in fact, I can even indicate, say the reason. Right, but let's add another statement. F is flat if and only if f prime is flat. In fact, for this statement here, we don't need quasi-compactness for G's. That's true whenever the base change G is basically flat without assuming it's quasi-compact. Why is this? Well, flatness is an affair that we can check on the fibers at the stalks of the sheaves at a given point. And if as x prime goes to x is surjective, s prime goes to s being surjective, x prime goes to x is surjective. We have only to prove the following thing. If A goes to B is a homomorphism of local rings, a local homomorphism of local rings, and if B is flat over A, let's rather call it A goes to A prime. And if A prime is flat over A and hence spacefully flat, then a module M is flat over A if and only if M prime is flat over A prime. All right, of course we know that if M is flat over A, M prime is flat over A prime. Let's prove the converse. We have to prove that for every injective homomorphism from N goes to N1, we have to prove that M tensor N goes to M tensor N1 is injective. And because A prime is faithfully flat over A, we have only to prove that after making base change in this arrow, it becomes injective. But what we get from base change is this here, which is reduced from N prime goes to N prime 1 by tensoring it with M prime. But N going to N1 being injective, this here is also injective because A prime is flat over A. And therefore, as M prime is flat over A prime, this is injective. In fact, not only flatness of modulus descends, but also faithful flatness of modulus descends. The same kind of argument. Now, on the other hand, to say that a morphism, that is sheaf F on this locally in space is locally free just means that it's of finite presentation and flat. And we know that finite presentation descends and flatness descends. So locally freeness descends. But of course, property to one's rank descend too, because the rank is a locally constant function on X, and taking this rank is compatible with taking inverse images. On the other hand, to say that a certain function on X is constant when X prime goes to X is surjective means that the inverse image is constant. And these two functions that have the same value. So all this is pretty clear. All right, so this was mainly fineness properties that we have descended so far. Now we are going to descend some slightly less trivial topological properties. You will find properties and set-theoretic properties essentially. Now let's descend some topological properties. Now here, the main result of which all the rest follows is a result of the following type. So we have, let's first set the situation. We have a morphism G from S prime goes to S. We have a subset Z of S. And we would like to know whether the inverse image of Z in S prime, whether its closure is equal to the inverse image of the closure of Z. Of course, what we always do have is an inclusion, namely that the closure of the inverse image is contained in the inverse of the closure. In other words, the image of the closure is contained in the closure of the image. But this is always true. What is not so clear is the opposite. And in fact, for the equality to hold for every Z just means that the morphism G is an open morphism. This is pretty trivial to check. So this property that we are interested in characterizes open morphism. Now flat morphisms are quite close to open morphisms. We have seen that flat morphisms of finite locally affine presentations are open, and on the other hand that flat morphisms have some property very close to the one of being open morphisms, maybe they are generalizing. However, we have seen also that flat morphisms are not necessarily open. For instance, the inclusion of a general point of S into S when S is reduced is flat, but certainly not open, except in very special cases. All right. Therefore, we can expect this equality to hold if G is merely flat without some restriction on the set Z. And now the restriction will be the following. Z should be the image of a quasi-compact morphism. So therefore, I will write down a quasi-compact morphism, and Z instead of being a subset of S will be a scheme lying over S, and I give myself a morphism, how we will call it, F, let's say, from Z into S, and I'm looking at the subset F of Z of S. And now the sum is the following. If G is flat, and if F is quasi-compact, then the relation here is true, then G minus 1 of Fc bar is equal to G minus 1 of Fc bar. So for these subsets of S of somewhat special type, but well, that makes a lot of subsets already. The relation that we're interested in is true. Taking closures commutes with inverse images. Now let's prove this. So we can assume, I see two ways of proving it, which are very related. We may assume, of course, taking closures is something purely local on S and S prime, so we may assume S and S prime to be affine. So therefore, the situation here corresponds to a homomorphism of rings A goes to A prime. On the other hand, we may also assume that S is reduced to the closure of Fz, because otherwise I just replace S by the closure, and I take S and S prime the inverse image of this closure, and the assumption that S prime goes to S is flat is still true after base change. Therefore, we have the theorem is reduced to the corollary, quite independently of reducing to the affine case, by the way, that if F is dominating, then F prime is dominating too. Maybe we should state that the converse is true. Converse, okay, if F is faithfully flat.
G.
If G is faithfully flat. Yes. let's see why is the converse true if G is faithfully flat. Assume F prime is dominating. All right. Then if G is surjective, therefore dominating, G F prime will be dominating. Is this clear? Let's see. Yes. If the image of C prime and S prime is dense, and if G is surjective and continues, then the image by G of this image here is dense in S. And therefore this composition is dominating. Approximately this is dominating. Dominating means that the image is dense. But what we are really interested in is this implication, which holds true without assuming that G would be faithfully just dense. Now, what does dominating mean? We can also, of course, assume that S is reduced. All right?
Excuse me. You
Yes.
said that a continuous image of a dense subset is dense? Is that what you said?
Is it not so?
No, take a constant now.
Uh,
Take a constant now.
no, but surjective.
Oh, G is subjective.
So F was supposed to be compact. On the other hand, we are readily reduced to the case. So we will have to prove the corollary. And for this we are reduced to the case, of course, when S and S prime are both affine. Moreover, we can assume Z to be affine, because Z being quasi-compact over S and S being affine, Z is quasi-compact in the absolute sense. So it can be covered by a finite number of affines. Of course, we can replace Z by the disjoint sum of these affines. So we assume Z to be affine. And then, of course, we can assume S also to be reduced, because dividing out by the equivalent elements doesn't change the situation. And so now, the situation is the following. We have this homomorphism of rings. On the other hand, we have an algebra B over A, and we make the base extension in this algebra. And now we have to express that Z over S is dominating. But this means that the kernel of A goes to B is nilpotent, is formed of nilpotent elements. And if A is reduced, it just means that A goes to B is injected. But if A prime is flat over A, then this means that this implies that A prime goes to B prime is injective too. And this implies that spectrum of B prime dominates spectrum of A prime. So that's one way of seeing things. We can also see things in a slightly different way by giving a more topological proof. Namely, instead of assuming G flat, it's enough to assume that G is generalizing, which is one of the main properties of flat morphisms. And G being generalizing, this property here will be true. Taking inverse images by G of sets commutes with closures, provided we are restricted to subsets that are images of quasi-compact morphisms. And it can be proved, in fact, if you want, by essentially the same argument, but using the following thing. How should we do it? All right. Why not give a topological proof without reducing to the upper case and such kind of nonsense? And we are reduced to proving the corollary again.
In the theorem, have you assumed that T is surjective? In the theorem, have you assumed that T is surjective?
No. I don't assume that G is surjective. G is just generalizing, that's true. That's all. Now, so something weaker than flatness. And F is again quasi-compact. And I have to prove that if F prime is if F is dominating, F prime is dominating. That's what we have to prove. The converse being true, of course, if G is surjective, as we see. All right. Now, what does it mean that F is generating? That F is dominating, I'm sorry. That means also that for every loss, when F is quasi-compact, let's prove the following lemma. Let F go from Z to S be quasi-compact, morphism. Then F is dominating if and only if for every maximal point S in capital S, the fiber of this maximal point is non-empty. So for quasi-compact morphisms, to say that F is dominating just means that the maximal fibers are not empty. Of course, if the maximal fibers are not empty, this is that means that the image of F contains the maximal points, and as the set of maximal points is dense, certainly, so the image of F is dense, and therefore this inclusion, this implication is true without even assuming F to be quasi-compact. But now let's prove it in the other direction. When F is quasi-compact, and then let's see. Well, it's more or less the same proof as above, as you will see. We may, of course, assume S. We have to prove that if F is dominating, then the fibers at maximal points are non-empty. Of course, this is again a local assertion on S, so we can assume S to be affine. And by the same trick as before, Z being quasi-compact, we replace it by the union of finite number of affine sets that cover it. We can assume that Z also is affine. And so all we have to prove now is the following. If we have an algebra B over A, then on the other hand we can also, of course, assume S. Alright. Then spectrum of B is dominating over spectrum of A, if and only if the general fibers, so let's say if spectrum of B is dominating over spectrum of A, you have to prove that the general fibers correspond to non-zero rings. Alright. Now we can assume, of course, A to be reduced. This doesn't change the topological situation. And then to say that B over A is dominating means that A goes into B is injective. Alright. And now, what do maximal points of the spectrum correspond to? They correspond to minimal primes, P, and localizing with respect to minimal primes gives precisely the residual field already. In other words, the residual field at maximal points are just localized rings of A supposed to be reduced at the minimal primes. Alright? And now A goes to AP is flat, and therefore if A is contained in B, AP is contained in BP. In other words, BP is not zero. And therefore the spectrum of BP is not empty. Alright, and now we come back to this corollary. We have to prove that if F is dominating, then F prime is dominating, provided we assume G to be generalizing. So let's prove it. We have to prove that F prime is dominating, and therefore we have to prove that the fibers of F prime at any point S prime, which is maximal in S prime, is non-empty. But G being generalizing, a maximal point of S prime lies above a maximal point of S. Does it not? That's essentially the property of being generalizing. That maximal points are transformed into maximal points. And the fiber here is deduced from the fiber here by making the Bayesian form kappa S to kappa S prime. And as the fiber here is non-empty, the fiber there will be non-empty too. So, in fact, even in this more topological argument, I mean, in order to prove the lemma, we have used flatness somewhere. The flatness of of the residue field at a minimal prime where ring is supposed to be reduced. So our theorem is proved, and now we will give some corollaries. So I will state the corollaries assuming f to be flat, let's say, but I think most of what I will say will be true if you assume only f to be generalized. So one thing, so we have the morphism G, and assume now that G is not only flat but also quasi-compact. So in other words, we can take for Z S prime and for F we can take G if you want. Then the topology of G of S prime induced by S is a quotient topology of S prime. And therefore, as still more particular, if G is surjective, if G is faithfully flat and quasi-compact, then the topology of S is a quotient of the topology of S prime. Now, what does this mean? That the topology induced as a quotient topology, that means that if we have a subset of S prime, call it let's say Z, and if G is the inverse image of the subset of S, which means that Z is separated by the equivalence relation defined by G, if Z is equal to G minus 1 of GZ, and if moreover the set is the inverse image of is closed in G of S prime, if GZ closed in G of S prime id est GZ equals GZ bar intersects GS prime, then we have to prove that Z is closed. It's said. That's what it means. That's topology is a quotient topology. We know already that the morphism to the quotient set is continuous. A subset in G of S prime for this T is closed if and only if its inverse image in S prime is closed. That's how we usually express. But here, let's see. How does this work? I'm going to state that Z bar which is equal to the closure of G minus 1 GZ bar. I am going to write that this is equal to G minus 1 of GZ bar. That's the formula up here. And once, so this is true provided I prove that G of C has the property stated in the theorem. So, and if we do this of course will imply that this is equal to G minus 1 of Z, because GZ bar and Z have the same trace on G of S prime. That's the assumption here, which is equal to Z, and therefore Z is equal to Z bar. That means that Z is closed. So all we have to prove is that this formula holds, that then that we are under the conditions of application of the theorem. And now why is this true? We have to prove that's it. Oh, let's see, I'm a little confused, perhaps. No, it's the opposite. That's the opposite line. That's it. You have to prove that if the implication I wrote down here is the evident one. If the set downstairs is closed, then the inverse image is closed. You have to prove that if it's set upstairs, if the set upstairs is closed, then the set downstairs is closed. That's what we have to prove. So, yeah, that's what I wrote. All right. I'm a little confused. What did I write here? So I assume that Z is separated. I assume that Z is closed. And I wanted to prove that this implies, yes. So I assume that Z is closed. That set upstairs is closed. I want to prove that set downstairs is closed, namely that we have G of Z is equal to G of Z bar intersects with G of S prime. That's what I wrote down. All right. But now it's clear, you see, that Z being a closed subset of Z S prime, I can endow it with the induced reduced structure, for instance, and then the image of Z in S will be the image of a morphism that is quasi-compact, because the inclusion of Z into S prime, Z being closed in S prime, is quasi-compact, and the composite morphism is quasi-compact, and therefore this formula holds in because of the theorem. All right. So what I proved is, therefore, as a particular case, that if G is surjective and flat and quasi-compact, then the topology of S is a quotient topology of S prime. So the same would hold true if G is just generalizing quasi-compact and surjective. And of course, as the assumption in the case of flatness is stable under any base change, so we see that it's true that G is submersive, as I say, and the topology of S is a quotient of the topology of S prime. G is not only submersive, but universally submersive. This property remains true after any base change. Now let's give some more corollaries. So I'm again in the situation where the morphism, in the S morphism X goes to Y, I have the base change S prime goes to S, I call it G. I assume now G to be quasi-compact and faithfully flat. And I want to give some descent properties. And assume that F is open or generalizing or universally generalizing or universally open Let's look at these properties. Let's look at the morphism, at the property of being a closed morphism, and let's look at the property of being universally closed. And let's look at the property of being a homeomorphism onto, or the property of being universally a homeomorphism. All right. Now let's look at the same properties for f prime. I claim if any of these properties is satisfied for f prime, the same property is satisfied for f, and of course the opposite implication holds when we are dealing with universal properties. So if f has any of the universal properties that f prime has the same, I mean, it's clear by the definition of these universal properties. So all what we have to prove, what is interesting is to prove that if f prime has any of these properties, then f has. And of course, the universal case is reduced to the non-universal case, because universal case just means that the assumption which is made here on f prime is true of the value base change. So we apply the result in the non-universal case to the situation that used after base change. So really, what you have to prove is the following: if f prime has any of these four properties, then f has the same property. This is clear. So here again, we may assume that s is equal to y. Now let's assume that f prime is open, and let's prove that f is open. So we have to prove that if u is an open subset of x, that then f of u is an open subset of y. But let's look at the inverse image of f of u and y prime. Taking inverse images, taking direct images is compatible with taking inverse images. That's because of what we said about fiber product sensitivity. So f of u prime can be obtained by just taking the inverse image u prime of u and x prime and taking its direct image by f prime. Now if f prime is open, f prime of u prime is open. So then fu is a subset of y whose inverse image is open. But y prime goes to y, makes of y a quotient, endows y with the quotient probability of y prime. And therefore f of u was open already. And so this is about open. This argument is exactly the same with closed. Using that if u is closed, let's prove that f of u is closed, but u prime will be closed. F prime being closed, f prime of u prime will be closed. Therefore the inverse image of fu is closed, and therefore fu is closed. All right. Now a homeomorphism is just something that is bijective and which is, let's say, open. On the other hand, because f is surjective, because g here, or g lower y, let's say, because g lower y is surjective, f is surjective if and only if f prime is surjective. And on the other hand, because g lower y is surjective, we see easily that if f prime is injective, f must be injective too. So this we have forgotten here. Let's say if f prime is injective, then f is injective, and the base change is surjective. Why is this? Should we prove it? Well, I mean, we are reduced to it. Here the fibers are reduced. You have to prove the following, that if you have a scheme over a field, taking a fiber here, call it Z over some field K, and if after some field extension Z prime is reduced to a point, then Z is reduced to a point. Z prime is empty or reduced to a point, then Z is empty or reduced to a point. That's what we have to prove. But Z prime goes to Z is surjective, you see. So that makes it all right. So this settles the case of homeomorphism. And what about generalizing now, which remains? All right. Let's look at the induced schemes at the point x, and here at the point y below x. We want to prove that this must be surjective, provided that f prime is generalizing. But let's pick, as this is surjective, x prime goes to x is surjective. Therefore, there exists a point small x prime above small x. All right. And let's look at the point y prime below x prime. Now we have the localized schemes here. Here we have now a commutative square of localized schemes. We know already that this is surjective because of the assumption on f prime of being generalizing. We know that this is surjective because of the assumption on G to be flat. In fact, generalizing, of course, was enough. Or universally generalizing, I should say, of course. You need the universal property. All right. Therefore, the compositum is surjective, and therefore this compositum is surjective. Of course, this is surjective. Let's give some layers of this with the same assumptions. F is separated if and only if f prime is separated. F is proper if and only if f prime is proper. Why is this? To say that f is separated means that the diagonal of f, delta lower f, is a closed morphism. So that's something that descends well. And therefore universally closed if you want. So that's something that goes in here. Now that, to say that just now. Now let's also give another corollary. F is an isomorphism if and only if f prime is an isomorphism. Here really flatness is used. It's not enough to assume that the morphism G should be universally generalizing. Being an isomorphism is something subtler than just a property, a topological property, being universal of the morphism. It involves actually very much directly the local ring with all the equal elements. All right. So let's prove this. So of course we have only to prove that if f is such that f prime is an isomorphism, then f is an isomorphism. So we know already that f prime is a homeomorphism, therefore f is a homeomorphism. So the property of being a homeomorphism descends. And therefore we know also that f prime, of course where f is quasi-compact. Let's say f prime being isomorphism is f prime is coherent. Let's say it's f prime is coherent and therefore f is coherent. and therefore f star of Ox must be a quasi-coherent sheaf of rings on Y. And all we have to prove now is that Oy goes to f star Ox is an isomorphism of rings, of sheaves of rings. Because then f will be a homeomorphism, f will be an isomorphism for the sheaves of rings too. But taking the direct image commutes with flat base change. So the homomorphism deduced from this one after making this phase base change is just homomorphisms from Oy prime to f star Ox prime. And the assumption is that this is an isomorphism. So our homomorphism here becomes an isomorphism after making a phase flat base extension. So it was an isomorphism before. So if you put, so this means in fact that if you look at the base change functor for a phase-fully flat quasi-compact base change, which associates to every scheme x over S the scheme x prime over S prime, this functor is conservative. If an arrow over S becomes an isomorphism after base change, it was an isomorphism before. And here I've also seen that it's faithful. You have seen last time that hom x y goes over S goes to hom x prime y prime over S prime is injected. So this here. As a consequence also of that the fact of being an isomorphism descends, if f is a monomorphism, independently if f prime is a monomorphism. Because being a monomorphism means that delta f is an isomorphism. So it's reduced to this case. Let's see. So that makes a lot of the notions we have seen, which descend well. Now we have to, in order to go further, we have to speak a little about descent of sheaves now, of quasi-coherent sheaves. So let's say this would be the third section, descent of quasi-coherent sheaves and of subschemes. Let's first make a little preliminary, very easy statement. Assume simply that f, the morphism of base change that I'm considering, is faithfully flat and nothing more. And let's look at the functor, which associates to every sheaf of modules M over S its inverse image M prime. Well, in fact, we have already said that this almost the definition of faithfully flat. This functor is exact, and it's faithful and conservative. Being exact, to be faithful or to be conservative, amounts to the same. And faithfulness just means the following: if you have two sheaves over S, and if you look at the set of homomorphisms of M and N into N, and the corresponding the map which goes from this into hom M prime N prime, homomorphisms over S prime, that this map here is injective. That is, that homomorphisms from M into N are particular cases, if I dare say, of homomorphism from M prime into N prime. And of course, the next thing which we would like to know is, what is the image in here? What are the homomorphisms of M prime into N prime that come from homomorphism of M into N? If you have such a homomorphism of modules, if we have two modules M and N over S, and if if we have the corresponding homomorphisms, the corresponding modules m prime and n prime over s prime, we will say that the homomorphism u from m u prime, let's say from n prime to n prime, descends to homomorphism from m to n. If it comes from a homomorphism of m into n, which homomorphism will be uniquely determined? So we have here this first example of the question of descent. And now there's an evident necessary condition, which is as follows. Let's designate by s second the fiber product of s prime by itself over s. And let's look at the two projections, P1 and P2 of s second. Then, if we have a module m over s, and we take its inverse image m prime over s prime, then the two inverse images of m prime by either P1 or P2, which we could call m second 1 and m second 2, they are canonically isomorphic because m prime comes from a module m over s, and therefore its base change to s second is obtained by making the base change from s second directly to s, and this composite term is equal to this composite term. So m second 1 and m second 2 can be identified, so we just call it m second if you want. It's just an inverse image of m over s second. And therefore, and the same for n second, and therefore if we have a homomorphism from n prime into n prime, it gives us in two ways a homomorphism from m second to n second. Namely by taking the inverse image of u prime either by P1 or by P2. And of course, if the homomorphism which we have descends to a homomorphism from m into n, then these two homomorphisms between m second and n second are just the unique homomorphism from m second to n second deduced by base change from the homomorphism we have here. So in other words, we have an exact sequence. We have a sequence that is like this. There's a double arrow going from hom m prime n prime to hom m second n second. And the composite term of these two arrows with the arrow here are the same. In other words, this injective homomorphism here, so this is true in fact that we have this diagram whenever we have a scheme S prime over another S. In fact, it's true in any category that we have a fiber category over it, like modules over variable schemes. But we have seen that if F, the base change G here, is faithfully flat, then this map is injective, and therefore we can identify this here with a subset of the kernel of this pair of morphisms. So this set is identified through a subset of the set of all elements here having the same image by these two arrows. And now, the natural question which arises, is it true that the morphisms that descend, that the necessary condition for a morphism here to descend, namely the condition that the two images are the same, is also sufficient? In other words, is it true that this sequence is exact? If this sequence is exact, not assuming anything for the time being on the morphism G, not assuming it necessarily to be flat nor anything, if for every m and n this diagram is exact, namely identifies hom m n to the kernel of this double arrow, then we will say that G is a morphism of descent for the fiber category of, let's say, quasi-current modules over variable schemes. That just means that the necessary condition for a morphism to descend is also, the evident necessary condition is also sufficient. And that on the other hand, the U that descends U prime is uniquely determined, and this for every m and n. It's something that would make a sense for any fiber category, need not be quasi-current modules over variable schemes. And now, our main theorem is the following concerning descent. Assume that the morphism of base change G is faithfully flat, quasi-compact. Then G is a morphism of descent for quasi-coherent sheaves for over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi-coherent sheaves over variable bases. And then G is a morphism of descent for quasi And in fact, give a somewhat stronger result. It's a morphism of effective descent. I will explain what it means for quasi-coherent sheaves. Now, before giving the proof of the swim, which in fact you have more or less proved it already at the very beginning, in the affine case, at least. Let's state what this effectivity means. So, assume that you have a morphism of descent. Now this implies that a module M over S is known up to isomorphism if you know its inverse image on S prime, together with a little more, together with this isomorphism between the two inverse images, between M second 1 and M second 2. Because if we look at the category of all modules M prime over S prime, endowed with such an isomorphism, then of course the base change functor, which goes from modules over S to modules over S prime, in fact factors into a functor which goes from modules. I always assume, let's say, that you have been speaking of quasi-coherent modules over S into modules over S prime together with such, let's say, call it a clutching data. So let's call this mod CL. CL is the initial of clutching. All right. So we have certainly always, without any restriction on G, we have always such a functor. And in fact, the fact that G is of a morphism of descent for quasi-coherent sheaves over variable bases just means that this here is fully faithful. Because when we wrote that Hom Mn is isomorphic to the kernel by the natural arrow of Hom M prime double arrow Hom M second. In fact, this kernel is precisely the set of homomorphisms of M prime and N prime that are compatible with the clutching data. So the statement that G is a morphism of descent just means that this functor here is fully faithful, namely induces an isomorphism between the horns. And I mean, this means intuitively that an object on the left can be reconstructed by knowing its image in the right, up to isomorphism. And it's the same for homomorphisms. Homomorphisms between objects can be reconstructed. Here, when we know. So homomorphism between the images, and this homomorphism between the images can be taken arbitrarily. So this being so, we see that the category of modules over S can be identified to a full subcategory of the category of modules over S prime together endowed with clutching data. And now the question arises, which is this full subcategory? Which are the clutching data by module M prime over S prime, which ensure that the module itself now descends, namely that it is isomorphic with together with its clutching data to the inverse image of a module over S. So if some clutching data, if a clutching datum on a module M prime over S prime is such that M prime descends, we will say that this clutching datum is effective. And what we can say here is that the morphism G is a morphism of descent for the fibered category of quasi-coherent modules, if and only if it induces an equivalence between the category of modules over S, quasi-coherent modules over S, and the category of quasi-coherent modules over S prime, endowed with an effective clutching datum. And so all we have to do now in order to complete the description of modules over S in terms of structures over S prime is to give a criterion for clutching data to be effective. And now there is a pretty necessary condition for clutching data to be effective. and which is obtained by introducing this threefold fiber product. And introducing, you see the threefold product maps in various ways to the twofold product. You can, these various projections, call them Q1, 2 when we project onto the first two factors, Q2, 3, let's say, when we project it onto the two last factors, and Q1, 3 when we project it onto the one and the third. And now here we have P1 and P2. And of course, when we look at this composite of these three morphisms with these two morphisms, we just get, in 6 different ways, you get the three projections of S triple prime to S prime. So, therefore, if you look at the inverse images of M prime, having a module M prime over S prime, we have the two inverse images over S second. A clutching datum would just be an isomorphism between the two. But now, if M prime really is over S prime doesn't come from an M over S which is fixed, we will carefully distinguish between F second 1 and F second 2, even if we give an isomorphism between the two. I mean, there's a certain choice, there may be many isomorphisms. Anyhow, these are different distinct modules. And I can look at the inverse images of M second 1 and M second 2 on S third by these three morphisms. We may think that there are 6 different modules now on S third, but in fact, we get only 3 different ones up to analytical isomorphisms. Because you see M second 1, M second 2 are inverse images of the same module M prime over S prime by these two morphisms. The modules which get on S third by taking the inverse images of these by these morphisms can only be viewed as being inverse images of M prime by these composite, and there are only 3 such morphisms. So for M third 1, M third 2, and M third 3, these inverse images of M prime on S third by these 3 projections, as first, second, and third projection. All right, and now what we get is the following situation. If we have an isomorphism like this, then we can take the inverse image of this isomorphism by each of these 3 morphisms. And we get isomorphisms between taking this one between M third 1 and M third 2, taking this one between M third 2 and M third 3, and taking the last one between M third 1 and M third 3. So this here would be Q, if the clutching datum is C here, this would be Q1, 2 star C, this would be Q2, 3 star C, and this would be Q1, 3 star C. And it's pretty trivial to check that if the clutching data is effective, then it comes from a module M over S up to isomorphism. And if M prime is isomorphic to the inverse image of module M over S in such a way that the clutching data here is the canonical one, then this diagram must be commutative. Then this arrow is a compositum of these two. Maybe I should make an analogy, which is, I think, fairly familiar to the case when we have a topological space S covered by open subsets Si. Then in this case, S prime we would take for S prime the disjoint sum of the Si's. And we look at the map of S prime into S, which on each of one of these Si is just the inclusion. And assume we want to define, to construct on S some object which is of a local nature, like for instance a sheaf or a fiber space or such a thing. Let's say a fiber space, that's a more familiar setting which is described at length in Steenroth's book. So then just the same situation will hold, namely, first of all, if we have two fiber spaces over x over S, let's say x and y, so the fiber spaces now replace modules, but you could take sheaves of modules over a given sheaf of rings if you prefer. I mean, there will be no essential difference. But let's speak about fiber spaces, which is more familiar. Then to give a morphism from x into y, an S morphism, a continuous map which commutes with the projections to S, is the same thing to give these morphisms on the SIs in such a way that they match in the intersections. But this can be expressed also by saying, what does it mean that we give a morphism over each of the SIs, introducing the sum of the SIs and introducing the inverse image of x and y over S prime, call them x prime and y prime. This means that we give a homomorphism from x prime into y prime. And to say that these homomorphisms that are given over the SI match in the intersections just means the following, that if you introduce the fiber product of S prime by itself over S, which is just the disjoint union of the fiber product of Si and Sj over S, for variable indices Si and J, which is just the disjoint sum of the intersections Si intersects Sj. And if you look at the inverse images of x, y over S second, x second and y second, so these are the fibers, these fibers over S second are just the set, essentially the set of restrictions of x and y to the Sij's. Alright, then a morphism from x into y is just a morphism from x prime into y prime, such that the two inverse images from x, which are morphism of x second into y second, are the same. In other words, this means that we get a fully faithful functor, which goes from the category of fiber spaces over S into the category of fiber spaces over S prime, endowed with clutching data, just as I explained there, endowed with an isomorphism of the two inverse images of x prime over S second. And that's it, that this functor is fully faithful and therefore identifies topological fiber space over S to a subcategory, full subcategory of the category of fiber space over S prime endowed with clutching data. And now the question is, what are the clutching data that are effective, namely what is the essential image of this functor? Namely, when is it true that if we give ourselves a space S x prime over S prime, which is just the same thing as a family of spaces xi over the SIs, and if we give an isomorphism between the two inverse images x second 1 and x second 2 of x prime over S second, which just means that we give isomorphisms between xi restricted to Sij and xj restricted to Sij. We give isomorphisms between the restriction of xi over the intersection Sij and xj restricted to Sij. When can we say that this datum, this clutching datum, allows us to reconstruct an X? And the answer is well known. It means that if and only it is true, if and only if the threefold intersections Si, Sj, Sk, for every triple of indices, a certain transitivity holds, namely that, which is exactly the transitivity which I have written down there. If you have the intersection Si, Sj, Sk, and if you look at the restriction of xi to it, of xj to it, of xk to it, alright, then we have, using the clutching data for the pair j, for the pair ij, jk, and ik respectively, we get isomorphisms like this, and we want that this diagram should be commutative. Alright, now the situation is exactly the same here. And in fact, if we had more time and leisure, we could reduce the notion of descent to something set theoretical, which is really close to this, yeah?
Are we trying to construct a morphism U prime, M prime, N prime? Is this it? We're trying to give conditions when the morphism, such morphism comes from a morphism of
We are supposed to have done it already. These are exactly the homomorphisms from M prime and N prime that are compatible with the clutching data. Maybe which are, you see this? If M and N are given over S, then the homomorphisms from M into N, they can be identified provided that G is faithfully flat and quasi-compact. They can be identified with the homomorphisms of M prime into N prime, which have the same image, which defined by the two inverse images functors P1 and P2, the same homomorphism from M second into N second. So this, I suppose, this was, to see, the conceptually more easy part, which I suppose that we have dealt with. So we assume that G is a morphism, not necessarily faithfully flat quasi-compact, some morphism for which this holds true for every M and N. Then we will say that G is a morphism of descent for quasi-coherent sheaves. And I have interpreted this isomorphism, which gives necessary sufficient conditions for morphism U prime between inverse images to descend, you see, and which gives unicity of this descent of morphisms. I assume this to hold. I have expressed it as meaning that a certain functor going from sheaves over S to sheaves over S prime endowed with extra structure is fully faithful. You see, the extra structure is the so-called clutching data. If M is a sheaf over S, the inverse image M prime has an extra structure, namely the two inverse images M second 1 and M second 2 of M prime over S second by P1 and P2 are isomorphic.
So descent is effective is equivalent to that condition. Full faithfulness?
No, that's a morphism of descent.
Just a morphism of descent.
So perhaps I should write it. That this here is an isomorphism, by definition, means that G is a morphism of descent for the fiber category of quasi-coherent sheaves. And I was about to explain what it means a morphism of effective descent. One offers, sometimes one says also that it's a morphism of one descent. That's perhaps nicer because a morphism of zero descent would be one for which from Mn goes to M prime N prime is always injective, for which this functor going from sheaves over S to sheaves over S prime together with clutching modules is a faithful functor. That would be a morphism of zero descent. A morphism of one descent is one level higher. That means that the previous functor is fully faithful. And now I'm about to define what it means a morphism of effective descent or a morphism of two descent. And when we are working with higher categories, of two categories, etc., there will be also morphisms of three descent, of four descent, etc. That is in fact a step-by-step increase of sophistication. So we are supposed to have understood, I don't know if this assumption is safe, what it means 0 and 1 descent.
Maybe the term gluing rather than clutching might be.
I do call it gluing,
Yeah.
gluing data, but it's not yet descent data.
Right.
Or gluing data perhaps.
In
What means to clutch then? I
In
thought
vector bundle theory, you call it clutching.
gluing. Gluing, yeah, recall long, gluing data.
In vector bundle theory, it's called clutching data. Say, for example, in the K theory, usual K theory is called clutching data. That is, you are given two bundles on hemispheres, and constructing a bundle on the sphere
Yes.
is done through clutching data on the
intersection.
intersection. That is-
Yes.
So it's vector bundle theory is usually called clutching data.
Yeah.
It's called recall long.
Recall
Recall
yes.
model.
So gluing, I think, is better than clutching.
Yeah.
Yeah,
Gluing,
I'm
yeah.
sorry. Yeah. I was thinking of gluing, but I just got it wrong. My English is poor. So I have to. So I wanted to explain for any morphism the S prime goes to S a necessary condition on some gluing data on a sheaf of bullets M prime over S prime, for this gluing data to be effective, namely to come up to isomorphism from an object M over S. And the condition is the condition I wrote down here, and then in order to make it more palatable, I gave the analogy here. And in fact, it's essentially the same thing, really. I mean, that's finally what comes out when one has understood descent. One has seen that it's essentially exactly what we do here. But the localization here, instead of being done by open immersions and taking a bunch of open immersions, is done here by morphism S prime goes to S, which is sufficiently to see big over S, so it's as good as an open immersion, as a family of open, surjective family of open immersions. That's the idea. Now, a gluing datum on a module M prime over S prime, namely an isomorphism between the two inverse images on S second, which satisfies this condition of transitivity, is called a descent datum. And therefore, what we can say is that in fact the functor which goes from modulus over S to modulus over S prime together with gluing data is in fact a functor which goes into the modulus with descent data. In other words, a necessary condition for gluing data to be effective is that there should be descent data. And now we will say that G is a morphism of true descent, or a morphism of effective descent, if this functor, which goes from modulus over S to modulus over S prime together with descent data, is an equivalence of categories. So let's give the definition in this case. Definition. G is of true descent for the fiber category of quasi-coherent modules over schemes if the inverse image functor induces a functor from modules over S quasi-coherent ones to modules over S prime endowed with descent data, call it mod dd, where dd is the initial of descent data, over S prime, but with respect to the descent data being taken with respect to S, that is the fiber products are taken with respect to S, if this functor is an equivalence of categories. So that's the definition. So we have 0 descent, 1 descent, and 2 descent. It's trivial that the morphism which is faithfully flat is of 0 descent for quasi-coherent modules over schemes. We have stated, but not proved yet, that if it's faithfully flat and quasi-compact, it's of 1 descent, and in fact, we now prove the stronger result with the same assumptions. If G is faithfully flat and quasi-compact, that then G is of true descent, in other words, the inverse image G star functor induces an equivalence between quasi-coherent modules over S and quasi-coherent modules over S prime endowed with descent data. I'm afraid that we have to stop. So let's start again in 15 minutes. So here again we have the same problem. Should we go along with these descent schemes? Is there other objections to yeah? Well, some general nonsense on groups. I think we could do it as well. No, anyhow, we won't give any structure to these one groups. We could just give some most general statements. So maybe it's better to well, I think the proof of sum is not so important, but to understand the meaning and how it's being used. You know, practically proved it already, by the way. We gave the proof.
So what would be 3%? You'd have a
3% would be Now, when dealing with this question of descent, in fact, there's so one difficulty is, in fact, just even on mathematical difficulties, one difficulty is psychological, and everyone has a kind of a hard time getting accustomed to the idea that one has been doing with moving data in topology, you see, just works exactly the same, and that the algebraic formalism is essentially the same. By the way, when people were working with moving data over topological spaces, they didn't take care either to check too much about compatibility of canonical isomorphisms, you see. But of course, the more remote you see the situation gets from something which one considers as being clearly a common intuition, you see, the more one feels the urge for writing down with care the mathematical logical foundations of the stuff. For instance, taking into account the canonical isomorphisms, that they are not identities, so that being careful not to confuse identifications with identities. You see. Now, when we want to write down the general nonsense about descent in general categories, you see, I mean, there's just, mathematical, there's really practically nothing. It's just general nonsense. When you try to do it with some care, then it's slightly messy, you see, because you get if you're not very careful, you get involved in this big mess of canonical isomorphisms, and you have to prove that there are no contradicting identifications that occur. Now, this general nonsense has been done in a little article of Giraud, Théorie de la descente. That's in fact the place where one refers to in order to feel safe, in order to say, well, proofs of the general nonsense involved have been done, but nobody, I think, ever reads this because it's pretty hard.
What is this published?
This is published in William Lawvere Société Mathématique about 10 or 12 years ago, I think.
It's in French.
It's in French, yes, to descent theory. It's pretty hard reading, you see. Unfortunately. I don't know if one can do a much better job as far as readability is concerned. If one wants really to do the things, not just make some hand waving as I have been doing. But anyhow, essentially, all kind of sums are proved in there, and maybe I will use one or two of them. But they're all kind of evident in a way. And that makes it, provided one is granting that canonical identifications are identities, you see, if one doesn't bother that with these matters, everything comes out practically trivially, the general nonsense. All right. So, including, the very basic notions that I have described so far. Now let's give an idea of the proof of the theorem. In fact, that the morphism which is spacefully flat and quasi-compact is a morphism of effective descent for quasi-coherent modules or variables. So I will scheme S prime over S, spacefully flat, quasi-compact. I look at the twofold product and at the threefold product. I have the category of modules over S, the category of modules over S prime, the category of modules, give them names, let's call them Fs if you want. Quasi-coherent modules over S, quasi-coherent modules over S prime, quasi-coherent modules over S second, and quasi-coherent modules over S third. I'm sorry, we have to consider them all, because we're dealing with two descent. And of course, we have between these the base change functors which correspond to the base change functor that we have below, not counting, by the way, other base change functors which I have not written. For instance, there's a diagonal. Here the arrows go in this direction. The base change functors go in the opposite direction. We have some more, by the way, like the diagonal morphism here. In fact, this here is a simplicial object in the category of schemes, an augmented simplicial object in category of scheme, and this would be something finite over it, which this would be a co-simplicial category in a way, you see. Every map from a finite set into another gives a function in the same direction between the associated categories here. So we have such a diagram. And it's in terms of this diagram here, of this co-simplicial category, which truncated at dimension 2 here, that we can describe the situation by saying that because we have such a thing, this functor here induces a functor from Fs to the category of objects here, endowed on x prime, endowed, or we put an m prime, I think, why not keep the same notation, endowed with touching data, namely an isomorphism between the two inverse images in Fs second by these two functors, and in fact it even induces a functor going from Fs to m prime endowed with not only not only with gluing data, but the subcategory of objects endowed with descent data, namely those gluing data which satisfy a transitivity condition here, n prime 1, n prime 2, n prime 3. Then this isomorphism deduced from this one by this base change, by this functor, composed with this isomorphism deduced from this here by this functor, should be identical to the isomorphism deduced from this one by this functor. Alright, and the situation we have in mind, what we want to prove is that we get in this way an equivalence between the category Fs and the category of these m primes endowed with descent data, and we mean data satisfying this condition. So that's the setup. And now, of course, first thing to notice is that this question is purely local on S for the usual Zariski topology. Namely, in other words, we can state it the following way: assume that we have an m prime over s prime endowed with descent data. In fact, for the time being, we don't even need to know whether they are descent data. It's enough to know that they are gluing data. And we want to prove that they are effective, but we assume that we know already that they are effective when we restrict the situation over open subsets Si of S that cover S. In other words, when we restrict the situation to such for an S alpha rather than Si, because the index I was already used here. We assume, therefore, that after restricting the situation to a situation over S alpha, we could descend m prime restricted to S prime alpha, let's say, the part of S prime line over S alpha, to a module m alpha over S alpha. Now this module is defined up to unique isomorphism, because we know already that our morphism, assuming that we know already that our morphism is a morphism of one descent. So that the solutions are unique, up to a unique isomorphism. And because of unicity, you see, of course, the restriction of m alpha to any close smaller open subset will still be a solution of the problem restricted to the smaller open subset. And therefore these m alpha over the variable S alphas will clutch together, will match together. And the thing that the module M that restricts to the m alphas in this way will of course be a solution to the problem of descending m prime. So in this argument I assume that we have proven already that the morphism was a morphism of one descent. Namely that if we could descend m prime at all, the descent was unique. Of course, in order to prove that it's of one descent, this also is a fortiori. I mean, that's still more trivial, is a local affair over S. Of course, we should have started perhaps with this. Because if you have a homomorphism, if you have two modulus M and N over S, assume we have a homomorphism from N prime to N prime. We want to see if it descends and want to prove that for it to descend it's self-sufficient, that it should be compatible with the descent data. All right, if we assume that we can cover S by open sets S alpha in such a way that restricting to the situation of S alpha, N prime alpha goes to N prime alpha, comes from a homomorphism from M alpha to N alpha, we know already that this homomorphism is unique because we know that this is of zero descent. And because of unicity, these homomorphisms that are given as alphas will match together and will give a homomorphism from M into N. And the corresponding homomorphism from N prime into N prime is equal to this one because it's equal to this one locally on the S prime alphas. You see. So I don't know if I have convinced you that it's enough to prove the same for small affine open subsets of S. In fact, I could refer to some journals of Giraud using the fact that a morphism from S bar, the disjoint sum of the SI's into S, is of effective descent for quasi-coherent modules, which is clear, which just means that quasi-coherent modules behave well with respect to localization, and to give such a morphism of quasi-coherent modules or quasi-coherent modules, to give them globally is the same thing as to give them locally together with conditions on the two-fold intersections, respectively, on the three-fold intersections. And therefore, I mean, the general nonsense reduction would be to say that if we have such a morphism which is of effective descent, we want to know if this is of effective descent. That's enough to know that after base change by this it becomes of effective descent. And these kind of statements you will find in Giraud. Which now means, because S is affine, that S prime is quasi-compact. That means S prime can be covered by a finite number of affine sets. Now take the disjoint union of these affine sets, call this S prime bar if you want. Now S prime bar goes to S, is again faithfully flat and quasi-compact. And moreover, S prime bar is affine. And what I contend next now is that if you prove this theorem for this morphism S prime bar goes to S, then it's true also for S prime goes to S. This comes from the fact that this morphism here is such that the second morphism can be factored through it. And now that's a completely general nonsense statement. If we have two morphisms, S prime goes to S and S prime bar goes to S, and if the second one is of one descent or of two descent for a certain fiber category, let's say it's a fiber category of modules, in our case, then this one also is of one descent or of two descent. In fact, it works provided I'm, yeah, that's it. Should I give some indications about this, or should I admit this as general nonsense?
Don't insert a clue or anything?
No, completely. You see, for instance, assume S prime bar is equal to S. As a consequence, of course, the identity is always a morphism of effective descent. You see, that's a pure tautology. So this will show that if S prime over S has a section, then it's always of effective descent. And this is pretty trivial. It comes from the fact, if you want, we can say it in various ways. In fact, this category here of objects over S prime endowed with descent data, this depends only on the homotopy type of this semi-simplicial object. I mean, that's one way of seeing the things. And on the other hand, if S prime has a section over S, then this simple object is equivalent to S. That's one way of stating things. But let's be more specific. We already did this, by the way, in the case when S prime and S bars are fine. I already stated the same things. So I'm kind of repeating the same kind of general nonsense. So remember, we had a ring A, an algebra A prime over A. And we wanted to reduce, we had a module M prime over A prime endowed with precisely descent data, namely with an isomorphism between M second 1 and M second 2. So two inverse images in A second equal to A prime tensor A prime. And satisfying a certain transitivity condition on the threefold tensor product. And if A prime is faithfully fit over A, then we give an argument showing that N prime comes in an essentially unique way from a module M over A. And the argument was to reduce to the case when A prime over A had a section, and then forgetting about the fact that A prime was flat. And then then we kind of say that it was trivial, and I think I tried to show why. You see, for instance, let's take first this case of something that has a section. Perhaps let's emphasize slightly on this. So let's first prove that if it has a section, then the functor which goes from Fs to Fs prime is faithful. So that is zero descent. That's the morphism of zero descent. In effect, if it has a section, then we have this cumulative diagram here, and if we follow the functor of base change from S to S prime by the functor of base change from S prime to S, we find, of course, here up to isomorphism identity functor. So this functor followed by another is identity, and therefore followed by another it's faithful, and therefore it was faithful before. Now what about fully faithful now? I'm sorry, fully faithful from objects over S to objects over S prime together with gluing data. So we have to prove that if we have two objects M and N over S, and if we have a homomorphism from N prime into N prime, such that this homomorphism is compatible with the gluing data, that it comes from a homomorphism of M into N. All right, we are looking for a homomorphism from M into N, and we hope that if we have found one canonically, kind of, that it will do. And now we take the inverse image of this homomorphism by the space change. We get the homomorphism from the inverse image of M prime on S, which is just M, to the inverse image of N prime on S, which is just N. So we have a means, because of the section, to construct the homomorphism from M into N, and then it's, just a few lines of computation to show that because M prime goes to N prime is compatible with the gluing data, that M goes to N, has as an inverse image precisely this. Because in fact what we can say is that the corresponding homomorphism from M prime into N prime is also compatible with the gluing data, and moreover it coincides with this one over the sections. And so all we have to show is that if two homomorphisms are compatible with gluing data, and if they're the same over the section, then they must be the same. And that's, I think, pretty little checking. And now what again? So let's not dive into this anymore, but what now if you have a morphism M prime over S prime? We don't know as yet if it comes from if you have a module M prime over S prime. We don't know as yet if it comes from a module over S. But M prime is endowed with gluing data and even with descent data, something stronger. And we wonder whether it comes from some M which we have still to construct. So what we do is we take the inverse image of M prime on S, call this M, and then we can manage to prove that the inverse image of M on S prime is isomorphic to M prime. Because the gluing data we had on M prime were descent data. You have to do this, of course. And here there's some algebra involved. But it's no nonsense. It has in fact nothing to do with modules, with rings, with nothing. It's just category theory. Because all I have to use is that I have here a semi-simplicial. That I have a semi-simplicial category. In fact, I can forget about these objects. They are just letters, you see. what really matters is this diagram, which is a semi-simplicial category, or co-semi-simplicial category, and everything can be expressed in terms of this. All right, and now let's come to, oh, I'm sorry, I shouldn't have erased Fs, Fs prime, Fs second. Now, let's come back to the situation when we have not S itself, which can be morphed into S prime by an S morphism, so that we have a section, but something slightly larger perhaps, S prime bar goes to S, but so that we know already that S prime bar goes to S is a morphism of, let's say, 2 descent. You see? And assume that after applying this base change, we can say it this way, call it S bar instead of this perhaps. Assume that S bar goes to S is of 2 descent for the Hilbert case we consider, and assume that after making a base change, by S bar, so we get an S prime bar, S second bar, S third bar here. We get a section of S prime bar over S bar. That's just equivalent to saying that we have a morphism, S morphism from S bar into S prime. That's the same thing as to give a section of S prime bar over S bar. But then this means that then I claim that S prime goes to S must be also of 2 descent. Why is this? Well, I will give the argument. So should we start with 0 descent and then go to 1 descent and 2 descent, do it more carefully, or should I just do it with 2 descent at once? Let's give the argument. It's just the same as the argument which showed us that if it's effective locally on S and it's effective globally on S. This was the case when S bar was just a disjoint union of open sets Si, you see. But now I have this marginal situation. But I mean, if we had wanted to prove really completely the case with Xi's, which you more or less admitted, I mean, we would have run in exactly the same diagram as here. And now let's say the idea is the same. Assume that we have an A prime over S prime together with descent data. We want to prove they're effective. We want to construct an M over S. Now, we look at the inverse image of M prime on S prime bar. Because M prime has descent data with respect to S, M prime bar will acquire descent data with respect to S bar. And therefore this M prime bar comes, and we assume on the other hand that there's a section here. And therefore this is of effective descent. Therefore this M prime bar comes from an M bar over S bar, which is defined up to unique isomorphism. Alright, now I want to show that this M bar can be descended to S in a canonical way, and the M which I will get on S will be a solution of our problem. So in the particular case we have dealt with before, just meant that the MI's which I constructed with this I in the intersections they match. Now let's make the argument if you want. We introduce S double bar, this Hilbert product of S bar by itself over S, and we have to define an isomorphism between the two inverse images of M bar on S double bar. But we have, of course, taking now the base change by S double bar to S, we have S prime double bar here, and we have S second double bar. We have a big diagram, I should perhaps write it again more carefully. We have S, S prime, S second, S third, and here we have S bar, S double bar, S triple bar, and here S prime bar, S second bar, S third bar. This is just, this line is induced from this line by making the base change. And the same with S double bar now. We make the base change like this in this line. Get S prime double bar, S second double bar, S third double bar, and the same here with triple bars. I don't know how many we will use. Let's write the whole diagram. And of course, I mean the situation is at this level is symmetric with respect to the diagram. We have also these homomorphisms here. So here a nice bisimilitude, simplicial object in the base category. Fine. And let's be. All right, I started here with a more intricate two-descent question, assuming already that one node and one descent was already settled. I could have started, of course, with zero descent and then one descent, because 0 and 1 descent are needed in order to deal with 2 descent. But I assume that 0 and 1 descent have been dealt with. So we have an m prime over s prime, you see. I recall, with descent conditions with respect to s, we are looking for an m. So I take its inverse image on s prime bar. This descent, which is deduced from this line here, is deduced from this line by just taking the space change, because m prime had a descent datum with respect to s prime over s. M prime bar has a descent datum with respect to s prime bar over s bar. Now this was assumed to have a section. All I need to know is in fact that it's of effective descent, and therefore I know that m prime bar descends in a unique way to an m bar. Now let's look at the inverse image of m bar, the two inverse images of m bar by these two arrows, called an m double bar 1 and m double bar 2. I am going to define an isomorphism, a canonical isomorphism between the two. So that's the gluing data. In order to see this, I look at the inverse images on S prime double bar, you see, call these two inverse images M double bar prime 1 and M double bar prime 2, you see. In order to define isomorphism there, I need only to define isomorphism here, such that the two inverse images here become the same, because as this has a section over there, this has a section over there. And therefore it's of one descent. But in fact, if you don't have section, all I had to use is 2 descent here and 1 descent here. All right. So I have to define an isomorphism like this. But you see, when I look, that's it. Yes. Now, if I have look at these two inverse images of these two modules by this morphism, it's the same thing as the inverse image of this module by these two compositae. Is it clear? By transitivity of inverse images, which is the same as these two compositae. But that's the same as taking the inverse image of m bar and 2m prime bar and taking the inverse image by these two compositae. But these are isomorphic because m prime bar comes from m prime. Is this clear? All right. Therefore, we get the isomorphism here. Now we have still to prove that this isomorphism is compatible with the gluing data. All right. Now you see, I guess you get the idea. And of course, this comes from the fact that, what should I say here? Can I say things in a nicer way, perhaps? Because then I have to say more. I have to prove that this gluing data, once I have done this, is in fact a descent data. You see, and for this, I have to prove that there are certain isomorphism holds here. But I mean, it's kind of messy to write it down in detail. It would have, if I wanted to do it really carefully, it would take us some time. But it's, you see, there's some diagram chasing, which, when it comes to the worst, you see, for 2 descent involves a diagram like this. I think you can. I think it's better to do these things at home, in a quiet corner. So let's not insist more on this. I hope to have convinced you that it's kind of obvious, but one just has to write it down. Alrighty. So this is the case we have considered. You see, reduced us to the case where not only S but S prime also is affine. But in this case, it's just a situation of a ring A and in algebra A prime over A. Quasi-coherent sheaves just correspond to modules over these rings. Fiber products of schemes correspond to tensor products of algebras, and so it's just a condition. It's just a situation here. We have to prove that the functor which, when A prime is a faithfully flat algebra over A, the functor which goes from modulus over A to modulus over A prime endowed with descent data with respect to A is an equivalence of categories. And there I have proved it a month ago or so. And here again, I mean, it was much the same proof, you see, using this kind of diagram. What we use is that if you, after base change, I goes to I bar, which isn't, no, it was not quite the same though. All right, the fact that it's of one descent is pretty easy, you see. So what's a little more delicate, which comes from the fact just that this here is exact, it remains exact. When we tensor by M. But no, that's not. So what is a little more subtle is that to prove effectivity, and if we have an F prime over A prime with descent conditions, namely descent data, namely with an isomorphism like this, satisfying the transitive condition there, then it descends. And the argument I remember was the following: assume that's it. I will take. I have already a module M over A, which is a candidate for the descendant module. Namely, of course, I have two morphisms from M prime into this same module. Identify M second 1 and M second 2 because of this isomorphism, call it M second. And I have, of course, two morphisms from M prime into M second, coming from considering M second as a base change for M prime by either of these two base changes. And let M be the kernel of this verbal arrow. And all I have to prove now is that the map which goes from, because we have an A-linear map from M into M prime, this can be viewed as being a homomorphism from M lower A prime. So base change in M from A to A prime into A prime. And because the way in which we choose M as being formed by points of M prime which are stable by descent, so to say, this will be a homomorphism, this will be a homomorphism which is stable under the descent data, compatible with descent data, and all we have to prove is that this is an isomorphism. So that's a problem. Now if we know that after a faithfully flat base extension it becomes an isomorphism, then it was an isomorphism before. And now we take as a base extension A bar equals A prime. But after this base extension there is a section and therefore it's of effective descent. And therefore then there's no problem. So that's the proof essentially. So I think it's really a very simple term. You see it. Algebraic, it involves a little general nonsense on categories, I mean, which we have to assume anyhow in this. And the rest is just some very easy playing around with flatness. So this theorem therefore we will assume to be proved now. So that's the first main theorem about descent. When we are really dealing with effectivity conditions. Now let's give a few corollaries. Let's assume that we have a sheaf quasi-coherent on S. Let's look at inverse image on F prime and the inverse image on F second too. Let's call it F second. And now whenever we have a subsheaf of F which is quasi-coherent, this defined as a subsheaf of F prime that is quasi-coherent. And whenever we have a subsheaf of F prime that is quasi-coherent, taking its inverse images by either of the two projections, we get in two ways a subsheaf for f second. So we get a diagram like this, subsheet of f going into subsheet of f prime, going into subsheet of f second through a double arrow. Now, we know already that this first arrow, assume now that s prime goes to s, is basically flat and quasi compact. We know already, because of mere faithful flatness, that this map is injective, because the Funke inverse image is exact and faithful. A sub-object is known, and we know its inverse image. So this here is injective. But if you have more about quasi compactness, I claim that this diagram is exact. Maybe that subsheet of f can be identified with subsheet of f prime, whose two inverse images on f second are the same. Now let's prove it. As a corollary of the theorem, this is exact. Let's look at the subsheaf g prime of f prime. And it has two inverse images, g second 1 and g second 2 in f second. And to say that they are the same, in fact, just means if you view f prime as a sheaf of s prime together with descent datum, then together with the isomorphism between the two inverse images of f prime by p1 and p2, and in fact we have identified these two inverse images by f second. The fact that these two are equal just means that g prime is stable in f prime by the descent datum. The descent data give an isomorphism between the two inverse images of g prime on s second and g second 1 and g second 2. And the identity, if you identify both as being subsheets of f second. And of course, when we see something which is induced, a gluing data that is induced by descent data, it must be again a descent data. I mean the transitivity on S third being true in f, when we look at the sheaf f prime f second f third, must be true also for subsheets. In other words, g prime comes from a quasi-coherent sheaf g on S together with the descent data. And because we have a homomorphism from g prime into f prime coupled with descent data, this homomorphism comes from homomorphism from g into f. On the other hand, after making the base change, this homomorphism becomes injective, so it was injective before, and we are through. So here I took it easy and used, the theorem in the strongest form of effective descent. I think that we could have done it without the general nonsense on descent, because just descending subsheaves or submodules in the context of political algebra would be little simpler. May involve less of the general nonsense on descent. But anyhow, it comes out very nicely like this. Now let's give another corollary. When we replace subsheaves by subschemes, let's look at subschemes of S. They define subschemes of S prime, and they define subschemes of S second in two ways, by taking the two inverse images by the first and the second projection. And can I descend subschemes here? Not all subschemes, in fact. Yeah. Take only the subschemes that are such as the inclusion morphism is quasi-compact, retro-compact, let's call them. For these, we have an exact sequence like this. Of course, retro-compactness of subschemes is stable under base change. And the same thing if we take closed subschemes, gosh, F is in the short term, not of closed. closed subschemes of S goes to closed subschemes of S prime, goes by 2 arrows to closed subschemes of S second. This again is exact, and the same is open. These three sequences are exact. Now let's see. Let's first take open subschemes, which is the most trivial. That just means that if you look at open subsets of S, goes to open subsets of S prime, goes to open subsets of S second, that this is exact. Now, before taking subsets with an openness condition on them, let's take arbitrary subsets. But subsets and subschemes have the same initials. So in French one says partie. So let's put P if you want. PS subsets of S, PS prime subsets of S prime, and PS second subset of S second. This is exactly like saying. A subset, of course, a subset of S is known when we know its inverse image because S prime goes to S is surjective. And I claim, only using that S prime goes to S is surjective, that a subset of S prime comes from a subset of S if and only if its two inverse images and second are the same. Of course, it's necessary. So we have only to prove that it's also sufficient. But what does it mean that a subset of S prime comes from a subset of S? That means that it's stable under the equivalence relation defined by this set sorted net S prime goes to S. That means also, now what is this equivalence relation? It's the fiber product of S prime as a set over S as a set by itself. All right, and as we have seen, the map which goes from the set S second to S prime factors, of course, I mean the two maps, of course, which we have, therefore define a map from the set S second to the fibered product of the sets S prime over the set S, like this, and we have seen that this here is surjective. Therefore, to say that a subset S prime of S prime has the same inverse image in S second means that they have the same inverse images in the fiber product by the first and the second projection, which just means that the subset is stable under the equivalence relation. So the exactness here is true already, assuming only that G is surjective. Now that we have the same exactness with open sets just means that the subset of S is open if and only if its inverse image is open. But this means that G turns S into a quotient space of S prime. This just means that the topology of S is a quotient topology, which seems to be true if G is surjective, if G is spatially flat and quasi compact, which we assumed F to be, which we assumed G to be. And the same thing, of course, taking to complements, we see the same thing with closed sets. Closed subsets of S can be identified with closed subsets of S prime that have two inverse images in S seconds the same. All right, so that's the set sorting aspect and topological aspect. Now, open subschemes, they just correspond to open subsets. Therefore, by taking them to structure, therefore this must be exact. What about closed subschemes? They just correspond to closed subschemes of S that just correspond to quasi-coherent subschemes of OS. And the same for S prime and S second. And therefore, this here is a particular case of this here. Now we have to take the case of arbitrary subschemes, and there I unfortunately have to restrict to the case of subschemes that are retrocompact. But of course, if the schemes S prime, S second are locally uniform, which is not too strong a restriction. Then every subscheme is retrocompact, so it's not too bad a restriction. I don't know if this exactness is true without the retrocompactness assumption. You will see it's true whenever S prime goes to S as an open morphism. If it's taking inverse images of sets communes with curves, by the proof I'm going to give. But if you assume neither an assumption nor that G is, let's say, a fine presentation, and I don't know if this exactness holds true. So you ask for an open problem. It's not very exciting. I solved for 10 minutes or so and just couldn't, or half an hour, I just couldn't get it. All right, now let's give the proof here. So, of course, we know that all that is injectivity, and we know that this diagram, that these two arrows equalize, that this arrow equalizes these two arrows. So all we have to prove is that if we have an element in here, such that the two images in here are the same, that it comes from here. And see, maybe I should make a little, yeah, maybe I should say why this here is injective. Maybe I didn't say it yet. So that's true whenever S prime goes to S is faithfully flat. It need not be crazy compact. Then two subschemes of S, a subscheme of S is known when we know the inverse image. T goes to T minus 1 T from subschemes of S to subschemes of S prime is injective. Why is this? Well, in fact, it's true. Yeah. A subscheme is known, of course, when we know it. When we know it on the local, when you know it, its restriction to the localizations of S, and so far we can assume S to be a local scheme, and then, of course, taking a point above the centrum of this local scheme, we can assume that S prime is local also, and therefore we are reduced to the quasi compact case. And then we should say the following: if F prime is quasi compact and faithfully G, I'm sorry, is quasi compact and faithfully flat, then the Lagrange goes from subobjects of S to subobjects of S prime is injective. Subobjects, by this I mean schemes T goes over S such that the structural map is a monomorphism. Why this? I should have said it before, in connection with isomorphisms descending. Because if you have two subschemes T1 and T2 in S, two subobjects T1 and T2 of S, which become equal, that means that if I look at the intersection of them, that the inclusions of these in T1 and T2 become isomorphisms after we make the space change. But that means that there were isomorphisms before, because the property of being isomorphism descends, which means that T1 intersects T2 is equal to both T1 and T2, so that T1 and T2 are equal. Of course, the same argument would apply with respect to inclusions. In order for T1 to be contained in T2 is necessary and sufficient that T prime 1 should be contained in T prime.
So couldn't you have assumed that S is affine, and then you're dealing with closed subschemes?
But they are not subschemes, they are just subobjects here. In this case, the subobject is known when I know its inverse image after faithfully flat quasi compact base extension.
Subobject means immersion, isn't it?
No, a monomorphism only. So let me give examples of subobjects which are not inversions. Take, for instance, the affine line you see, and now take the complement of the point in the affine line, union, the disjoint sum of the complement of the point and the point, and look at the morphism of this into the line. It's not an inversion, you see, but it's a monomorphism. we can also, instead of a point, we can take an infinitesimal neighborhood of this point. The disjoint sum of this with complement of the point. We get a monomorphism. And there are many examples, interesting examples of monomorphisms, but this is the most typical one. Or also take a curve with a double point, you see. Now take its normalization, which is a non-singular curve. Now the projection from this is not a monomorphism, because over this point here there are 2 points. But cut out one of them, you see. So now the morphism can be shown of this curve minus 1 point into this one can be shown to be a monomorphism. On the other hand, you see, if it was, as it's surjective, it's bijective in fact, and the base is reduced, if it was an inversion, it would be an isomorphism, and it's certainly not an isomorphism. The right upstairs is normal, the one downstairs is not. It's not even a universal homeomorphism, as I showed you. You see. Because, I mean, what happens is that intuitively, you see, the branch which we have conserved, that's here, you see, it corresponds to just one branch here, you see. It's not universally open, you see. There's the other branch that is crossing us. So that's, and we see what happens, you see. The situation is reflected by what happens after making the base change, by just the normalization. And then precisely something like this appears. You see the isolated points that are appearing. That's what I explained a few lectures ago. All right, so what I am saying here about sub-objects is definitely more general than taking subschemes. I said sub-objects and not subschemes precisely, because subschemes has a more restricted technical sense already. Sub-object in the capital of schemes is not the same thing as a subscheme. It's something of more general than subschemes. All right, now this here sub-object in the capital of schemes, that's the inclusion relations between them is something that descends well by faithfully flat quasi-compact descent, and therefore this map is certainly injective when we are looking at subschemes, which are particular cases of sub-objects. Now all we have to prove is the following: if you have a subscheme Z prime of S prime, now it's really a subscheme. So for instance, the underlying set is a locally closed subset of S prime. And if we assume that the 2 inverse images Z second 1 and Z second 2 in this segment are the same, I want to prove that it comes as an inverse image from some subscheme Z of S. Now first thing is that I know already that Z prime as a set descends. The 2 inverse images of Z prime as a subset of S second are the same. Therefore Z prime is the inverse image of a subset Z of S. That's the example is here. Now next thing we have to prove, and that's here where we have to assume retrocompactness for Z prime. We have to prove that Z is locally closed in S. And in order to prove this, you look at the inverse image. You look at the closure of Z, and using our assumptions, we see that the inverse image of this closure in S prime is the closure of Z prime. Because you see, Z is the direct image of Z prime, and as Z prime goes to S prime is quasi-compact, and S prime goes to S is quasi-compact too. This means that Z prime goes to S as a compositor with quasi-compact. So Z is as a subset of S is the image of a quasi-compact morphism, and therefore taking closure commutes with taking inverse images by a flat morphism. So Z prime bar is just the inverse image of Z bar. All right. Now let's endow for a moment Z bar with the induced reduced structure, and the same with Z prime bar. And let's take for Z prime bar just the inverse image of this subscheme of S. All right. So then we have the situation here where we have a subset Z of Z bar, such that after making this base change here, which is a flat base change, you see, this base change here, which is a flat base change, that's it. its inverse image becomes open in Z prime bar. So therefore Z was already open in Z bar, because the topology of Z bar is a quotient of the topology of Z prime bar, which is basically flat quasi compact over it. Therefore Z is open in a closed set, and therefore it's locally closed. If you want, we could have written down here the exact sequence. You see, locally closed retrocompact sets in S can be identified as locally closed retrocompact sets in S prime, whose two inverse images in S taken are the same. That's true. You see, locally closed sets descend in the setup, provided they are retrocompact. Alright, so that's what we have proved here in fact. That's true when the base change is basically flat quasi compact. Alright, so that was the main point, that Z is locally closed. Now we are reduced to the case of closed subschemes, because Z can be viewed as being a closed subset of an open subset of S, U, and therefore Z prime can be used as being a closed subset of the open subset U prime of S prime. And now we can forget about S and S prime and replace them by U and U prime. And so we have a closed subscheme Z prime of U prime whose two inverse images in U second are the same, and therefore it descends to a closed subscheme Z of U. Because the case of closed subschemes have already been settled. This is here. So subschemes descend provided that we make a slight retrocompactness assumption on that, which perhaps is not necessary. Now I can prove the following. It reserves for the theorem that again G be faithfully flat and quasi compact from S prime to S. Then G is an morphism of descent, or maybe from descent of one descent, for the Hilbert category of schemes over schemes, of relative schemes. I will write down what it means. So that means the following. If I have two schemes X and Y over S, therefore I get schemes X prime and Y prime over S prime, and by inverse image, and also schemes X second and Y second over S second. I have a map which goes from hom xy over S to hom x prime y prime over S prime, and from this a double arrow as usual into hom over S second of X second into Y second, and the hom of X prime into Y prime by taking the inverse image either by the first or by the second projection here. We find the homomorphism from X second into Y second. And the statement is that this is exact. A homomorphism from X prime into Y prime descends to a homomorphism from X to Y, if and only if, well, it's stable with the descent conditions, with the descent data if you want, or what can be expressed by saying that it's two inverse images. U as homomorphism from X second and Y second are the same. And then the descent of morphism is unique. We have already seen that the morphism S prime goes to 0 is to of zero descent. Just keep over others. In other words, that this map here is always injective. The functor of base change is faithful. Alright, so all we have to prove is that if you have an element in here, such that the two inverse images over S second are then it descends. now let's prove this. Let's look at the Fourier product x times s over y, the product of x and y over s. Then, to give an S morphism from x into y is just the same thing as to give a section of x times y over x. And therefore, it's the same thing as to give a subscheme, call it Z, of x times sy, which is the property that the first projection times y prime over s prime with the first projection x prime. I assume given a morphism from x prime into y prime, or what amounts to the same, I suppose given a section of x prime times y prime into x prime, or what amounts to the same, I suppose given a subscheme z prime of x prime times y prime, such that the first projection induces an isomorphism here. And I want to show that this morphism descends, or what amounts to the same. I want to show that this subscheme, together with the isomorphism here, descends to subscheme here with an isomorphism here. But the assumption was that this morphism is compatible with the descent data, that the two inverse images of this morphism as two morphisms from x second to y second are in fact the same, so they correspond to just the same subscheme, z second, of x second times y second. So we have a subscheme of, give a name to this product x times y, call this p, p is the initial of product. So we have a subscheme of p prime, such as the two inverse images of the subscheme are one and the same subscheme of p second. And therefore, if we assume for a minute that this subscheme is retrocompact in p prime, which is a very small restriction, we can conclude that the subscheme descends to a subscheme z of p. Now what about the first projection, which induces the morphism from z into x? This morphism, after base change, becomes an isomorphism. So it was an isomorphism before. So we are through, except that we had to make some extra assumptions which ensure that the subscheme here was retrocompact, that this morphism here was quasi-compact. But for this, it's enough for y prime to be quasi-separated over s prime. And that's just what it, or for y to be quasi-separated over s, it just means that after any base change, any morphism of x prime into y prime, when interpreted as a section, is quasi-compact. All right. Therefore, if we assume quasi-separated, this is over S, this is proved. If y quasi-separated over S, which indeed is a pretty weak assumption. However, we want to get rid of this assumption because this is really an important result, and we don't want to have parasitic assumption in it. So this is pretty easy. So let's deal with the general case, assuming that we know it when y is quasi-separate or y is affine. Never mind. Now we forget about our diagrams with graphs. We have a morphism from x prime into y prime, stable with descent conditions. X and y are given over s. And we want to prove that this morphism f prime descends. We want to construct an f here. Now we cover f, we cover y by affine open sets yi. We can of course The question is purely local on S. We can assume S to be affine if we want. We cover now Y by affines, open affines, and therefore Y prime is covered by the inverse images of these Yi's, Y prime i's. And I look at the inverse image by F prime of Y prime I, which is an open subset X prime I of X prime. And because F prime is compatible under the descent conditions, because the two inverse images of F prime by the two projections are the same morphism from X second into Y second, it follows that the two inverse images of X prime I, which is an open subset of X prime, by one and the other space change are the same. Therefore, X prime I, in fact, is stable under descent, which means that it corresponds to an open subset Xi of X. There they are. All right. Now look at the induced morphism from X prime I into Y prime I. This, of course, is again stable under the descent conditions. And because now Yi is affine over S, and therefore certainly phase separated, it comes from a morphism from Xi into Yi. And of course, because of unicity of descent of morphisms, these morphisms from the Xi's, of course the Xi's cover X because the X prime I's cover X prime, and the morphisms from the Xi to Y, which I have constructed in this way, match together in the intersections. So what have we obtained so far? We can express it in the following way. Assume that S prime is quasi-compact and faithfully fed over S. Then, to give a scheme over S is the same thing as to give a scheme X prime over S prime, together with descent data with respect to S prime over S, namely together with an isomorphism between the two inverse images of X prime by the two projections, satisfying a certain transitivity relation on S third. Like this, such that these descent conditions should be effective. So when there is a pretty subtle condition of effectivity, what we can say is that we get a functor which goes from schemes over S into schemes over S prime endowed with descent data, and this functor is fully faithful. Therefore, I mean, the category of schemes over S can be identified to a full subcategory of the category of schemes over S prime endowed with descent conditions. So we can reconstruct completely a scheme over S when we know X prime over S prime together with this descent condition. But then, of course, that's what is expressed by this theorem here. But then, of course, the question remains, which are the schemes over S prime together with descent conditions which come from X over S after isomorphism, from some X over S after isomorphism? Or also, what are the effective descent conditions on relative schemes X prime over S prime? So I think we don't have time today to dive into this question. Let's only say that from what we have seen here about the effectivity of descent for modules, it will follow that the same is true for the descent of relatively affine schemes. Namely, the category of affine schemes over S is equivalent to the category of affine schemes over S prime endowed with descent data. All right, so this theorem here was obtained again as a corollary of this theorem still. But let's give another descent statement before finishing. So the assumption S prime goes to S is always the same, and we look at the morphism F from X into Y, and I claim that F is an open immersion, respectively a closed immersion, respectively a quasi-compact immersion if and only if f prime is. So the notion of immersions with the open or closed descends well, provided that we make, in the general case of immersions, neither open or closed, that we make quasi-compactness assumption. Here also I'm afraid that I don't know how to get rid. Maybe I should have said this. Well, anyhow, I mean, there are two corollaries of this statement about descent of subschemes. One is this corollary here, which is a more important one, and the other is this one here. Let's prove it. So I assume that after base change from x prime to y prime, and let's assume that we get a closed immersion from x prime to y prime. Therefore, x prime appears as a closed subscheme of y prime. And of course, the two inverse images of this as two subschemes of y second are the same, because they are just the inverse image of the subobject x of y by y second goes to y. Of course, x goes to y will be a monomorphism, because here we have a monomorphism. All right. Now we know that the subscheme has its stable and descent conditions, because that's it. Because it's a closed subscheme, we know that it descends to a subscheme. How will we call it? T, if you want, of y. And now we have two subobjects t and x of y, and they become the same after base change. So they were the same before. I didn't know as yet that x was a subscheme, but it's a subobject. You see, this is a monomorphism because we have a monomorphism after base change. All right, and therefore x is a subscheme of y, a closed subscheme of y, as t is. All right, this settles the case of a closed immersion, the same for an open immersion, the same for a quasi-compact immersion. All we have to use each time is that this kind of, the corresponding kind of subscheme is descent. If we take an arbitrary, hey, maybe we can deal with the case of an arbitrary immersion. Oh yes, I think we can. Now let's take the case of an arbitrary immersion. Of course, quasi-compactness also descends, so it would be nicer if we could with the case of an immersion. So assume that x prime goes to y prime is an immersion. And let's prove that x goes to y is an immersion. So we can, of course, assume y is affine. It's purely local question on y. And now x, I write x as being the filtering union of quasi-compact subsets of x. And x is covered by a possibly infinite family of affine open subsets, and I take the filtering union of all finite unions. All right, these finite unions I call xi. And now, therefore, x prime is just the filtering union of the x prime i's, isn't it? And because x prime goes to y prime is an immersion, on each of these open subschemes it induces an immersion. And therefore, by descent, each of the xi's goes into y is an immersion. And now all we have to prove is that if x is the increasing union of a family of open subschemes such that the induced morphisms from xi into y are immersions, then x goes to y is also an immersion. Which I think is kind of trivial. So a filtering union, I mean the main point is to prove that the image of x and y is locally closed. But the filtering union of locally closed subsets, each of which is, let's say, I guess it's true, isn't it? It's either trivial or it's false. Let's see, what would it be? We have a subset x of y, you see. This topology already we know now is induced by y, because, do we know it? Okay, perhaps not. the space X, it's a disjoint, it's a filtering union of open subsets Xi. And we have a map from X into Y so that the induces on each of these and homeomorphism onto a locally closed subset. Now, is it true? First of all, that's an homeomorphism into, by all means. Is it clear or not? So, we have to prove that each of the xi's, let's say, is induced by the inverse image of an open subset of Y. Gosh. I really don't know. I think that's...
Open or locally closed? Open or locally closed?
No, the xi's are open in X, but they are locally closed in Y, you see. The inclusion from xi into Y. Is homeomorphism onto a locally closed subset. Hey, it doesn't seem to be so drin. Can the
Take a discrete set. Yes.
yes. Let X be a discrete set, let's see.
Yes.
Let's see, yes. Now, so it's false, yes.
Yeah.
Yeah, it's false. Take a dense subset of the line, for instance.
Yeah.
So it's false as stated. So I don't, yeah, you're right. So maybe we better. So it's a problem then with it. Of course, the example that you gave, but of course it's false as this, I mean, this lemma which I wanted to state for schemes is false definitely, because the same example as you gave takes the disjoint union of all closed points in the line, you see, and takes the morphism from this into the line. On the other hand, yes. However, I think it's that inversions descend even without clearly compactness as assumptions, but I just can't prove it. But this, of course, would give another proof of the fact that isomorphisms descend, as particular cases of closed emergence. All right. So I guess tomorrow we will finish the general statements about descent. And effectivity criteria. Is a quotient topology of S prime. I would like to make a little side remark concerning a little lemma we proved in the to this effect. Remember that the way, some slightly stronger way in which we stated the thing was just assuming a G to be flat, not necessarily faithfully flat, not quasi compact. The question is a purely local question on S prime, but I'm going to say if F was a quasi compact morphism of some scheme into S, then taking the closure of the image commutes with space change by a flat morphism. Minus 1 of FC bar is equal to F prime bar. Or it wants the same. If you look at the image of Z and S, then the inverse image of the closure is the closure of the inverse image. And in order to prove this, we have stated we have proved a kind of trivial lemma, namely if Z goes to S is a morphism that is quasi compact, as before, then F is dominating if and only if the fibers of Z at maximal points of S are non-empty. So I want to give to this lemma an equivalent formulation. So F is as before, then a point S of capital S belongs to FC bar, I'm sorry, to the closure of the image of Z, if and only if there exists a generalization of S which belongs to f of z, if the spectrum, if the localization of S at small s intersects f of z. If and only if there exists a generalization of S that is an f of z. In other words, if and only if, that's the same thing, there exists an element T in f of z such that S is in the closure of T. Of course, if an element is in the closure of S is in the closure of an element of Fc, it belongs to the closure of Fc, so the only thing that is less tautological is that the converse holds. But of course, that's the corollary of what we said about the dominating case, because replace S by the closure of Fc endowed with, for instance, with the induced reduced structure. All right. So we can assume now that C goes to S is dominating, and all we have to prove then what's this nonsense? Let's see. That's it, yeah. Is that for every point of S, the property which we have stated is true. But take a maximal generalization of S, take a maximal point of small s that generalizes S. Well, its fiber is non-empty, in other words, it belongs to the image of Z. So I mean, it's just an equivalent formulation of what we said about dominating morphisms. So, so we have a very handy criterion for a point to belong to the closure of an image of something by a quasi-compact morphism. So it belongs to the closure of a set to which we apply some slight restriction, I mean that it's the image of a quasi-compact morphism. Of course, if we dualize it, if we take the complement of such a set which is a complement of such a thing, then we have a criterion for a point to be interior to such a set. Maybe it's necessary and sufficient that the localization of this point belongs to it. So let's take that A be f of z, and that B be the complement of f of z, S minus f of c. So we just have proved that Z is in the closure, that the point S of capital S is in the closure if and only if there exists S prime generalizing S such that S prime is an A, and dually we see that S is in the interior of B if and only if every generalization of S belongs to B, in other words, if the localization of capital S and small s is contained in B. So this is something I had mentioned more or less. So for sets that are reasonably non-wild, let's say, which are not too wild, we can characterize the points that are in the closure as being just the closure of the set, be just the union of the closures of the points in the set, and the interior of the set as being the set of points, all of whose generalizations are in the set. And now let's come back to a statement which I made about a generalizing morphism being open under certain circumstances. So let's assume now that the morphism F is generalizing, that is, the induced morphism on the localizations are surjective. And we wonder if F is open. We have seen that the converse is always true. Now, the question is purely local, so we can assume Z and S to be affine. And now what we know is that all we have to prove is that the image of Z in S is open, of course. Otherwise you replace just Z by an open subset. Alright, so we have to prove that the image of Z in S is open, S and Z being both affine. But what we know is that the image is stable under generalization. So it satisfies the condition put here, except that we don't know as yet whether that they have still to check the complement of the image is itself the image of a quasi-compact morphism. So if a set is such that it's an image of a quasi-compact morphism and it's a complement also, then we'll say that the set is constructible. So we know that the image of Z and S is the image of a quasi-compact morphism. We don't know it yet for the complement. So all we need now is to have a criterion which asserts us that the image of a given quasi-compact morphism is in fact constructible, that the complement also is the complement of quasi-compact morphism. Now this will be true whenever F is a finite presentation. And it's not hard to, in fact it's not hard to prove. Let's see how this goes. Well, by the general nonsense on passage to limit, we can assume when F is of finite presentation that in fact S and that S is Noetherian by reducing to a case the situation of finite type with integers. And then by Noetherian induction on S, all we have to prove is that if S is the maximal point of S, then either there exists a neighborhood of this maximal point which doesn't meet the image, or there exists a neighborhood which is covered by the image. And this again is a particular case. I mean, this is trivial characterization of constructible sets. It's a subset of a Noetherian scheme is constructible if and only if there is a point of it, and you look at the intersection of the set with the closure of this point, either this intersection contains the whole neighborhood of this, now inducing on this situation, either the set contains the set now contains a non-empty open set in the neighborhood of the generic point, or it is rare, or there exists a non-empty open set which doesn't meet it at all. Alright, so we have to prove this in this case when S is Noetherian and irreducible, that the image of Z and S either contains an open set or does not meet an open set. Alright, now we look at the generic fiber Z lower S. So either it's empty or it's non-empty. So we have to prove that if Z lower S is empty, then there exists the whole neighborhood of small s, such that the part of C lying over S is empty. But we know this is passage to limit, you see, because we know that the generic point small s is as a scheme the inverse limit of the affine neighborhoods that contain it. And if at the limit you see 0 s becomes empty, it was already empty at the finite stage. And in fact, the non-emptiness also is something that passes well to the limit. That's pretty clear. How should I say this? Maybe I shouldn't. Should I make it explicit that to prove that if 0 s is not empty, then there exists a neighborhood of a small s, the generic point, such that all the fibers are not empty? It's pretty easy to prove. Maybe to do it as an exercise. So this gives, pretty easily the fact that a generalizing morphism of finite presentation, local finite presentation, is open, which is very useful result. Remember that we have used it in order to prove that if x and y are schemes of a field, then the projection of x times y to y is open, without any restriction, otherwise on the schemes x and y. All right, so we have seen a number of properties for morphisms, for sheaves of modules over schemes, for morphisms of schemes, or for sheaves of modules over schemes that descend well by faithfully flat quasi-compact descent. So the situation was that we had a morphism of base change S prime goes to S, which was faithfully flat and quasi compact. We had a morphism F x to y. We looked at the morphism deduced from this by base change, and the statement is mainly where that F has a certain property, like being a closed immersion, an open immersion, a quasi compact immersion, like being proper separated of finite type or finite presentation, or locally of finite type or locally of finite presentation, and so on. I mean, quasi compact, quasi separated, coherent, all kinds of the whole bunch of properties practically which we have seen. F has one of these properties, it has only F prime has it. There was also the question of morphism to be universally open or universally generalizing, lots of things. Practically all properties have been obtained, I think, with one or two exceptions that we are going to deal with. So that's the yoga of descent, I mean the unsophisticated yoga of descent, without speaking of descent data and such things, which are slightly more sophisticated. Let me, however, give one counterexample of properties of morphisms that don't descend. It's the property of being projective or quasi-projective. If F is such that F prime is quasi-projective projective, we can't conclude that F is projective or quasi-projective. I mean, it's the same. The question for quasi-projective or projective is essentially the same question. So let's say projective. And this comes from the fact which I had pointed out, that the property of being projective is not even local for Zariski topology. You see, it's quite possible that F is projective locally over Y for the Zariski topologies, that can recover Y by open sets such that over each of these it's projective, and however F is not projective. Then of course we may take for Y prime the disjoint union of these open sets, and we get faithfully flat quasi compact morphism, which is such that F prime is projective and F is not. So that's something that causes some difficulties in descent theory. We have also seen that we can descend properties of shield of modules on S, let's say, or Y or X, that amounts to the same, because the morphisms here satisfy the same properties as here. Let's say it on S. A module over S is of finite type or finite presentation, if and only if the universe dimension S prime. Here this property, the same for locally free of finite type, the same for locally free of rank N, or invertible modules, etc. All these properties descend. You could also speak about properties of morphisms between modules, but I mean this is pretty evident in terms of the mere faithful flatness of S prime goes to S. And then we started to speak about descent data and effectivity of descent data. We stated that the theorem which is for the time being the main result in descent theory, that if S prime goes to S is faithfully flat and quasi compact, then it is a morphism of two descent, or if you want sometimes says also a morphism of effective descent for quasi-coherent modules. Which meant the following things by order of increasing strength. Zero descent just means that for every two modules M and N on S, Hom Mn mapped to Hom M prime and prime, where M prime and N prime are the inverse images on M S prime, is injected. So that's zero descent. That means that the functor going from modulus over S to modulus over S prime is a faithful functor. Now, one descent involves the Hilbert product of S prime by itself over S, call it S second. And one descent means that for every two modules M and N over S, I assume everything to be quasi-coherent. if you look at the diagram, hom mn goes to hom m prime n prime goes to hom m second n second by 2 arrows, where m second and n second are the inverse images of m and n over s second, the fiber product of s prime by itself, then this diagram should be exact. That's one descent. And it can be expressed by saying that the functor which goes, the base change functor which goes from modulus over s to modulus over s prime, now I will take modulus over s prime with extra structures, endowed with descent data, that this functor is fully faithful. 0 if you wanted to express it in a more sophisticated way. Using s second, you could say that's the functor which goes from modulus over s to modulus over s prime endowed with descent data is faithful. And now the same functor here should be fully faithful. All right. It seems, but I have not checked it carefully, that this is true. Even 1 is true if you assume only s prime over s to be faithfully flat without assuming it to be greatly compact. I have not written down carefully but the question was raised by one of the auditors, and it was a quite natural question, I think. The answer is. And now, what about 2 descent? Now in 2 descent, we have to introduce the threefold fiber products. And if you want to state it very coarsely, approximatively, and as an analogous statement to this, we would say that if you have a module over s prime such that the 2 inverse images over s second are isomorphic, then it comes from module over s. But this, of course, would be false. I mean, it's the kind of thing precisely. That's the first thing that may come to mind before one thinks over it, and that is the wrong thing to say. So we don't have an exact sequence like this with isomorphism classes, for instance, of modules. That would be completely wrong. What the next step would say is the following. Now we start with a module m prime over s prime. We give a descent data on m prime, namely an isomorphism between the 2 inverse images on s second, satisfying a certain transitivity condition on s third. So that's how s third is used. And the statement is that m prime, together with this descent data, comes up to isomorphism from a module m over s. So that means also that the functor which goes from modulus over s to modulus over s prime endowed with descent data relative to s prime goes to s is an equivalence of categories. And I mean, this progression suggests that perhaps there are situations where one has to introduce 4-fold fiber product and speak of 3 descent. But fortunately, we're not going to have to do this here. If you wanted to match together, you see topoi, for instance, instead of matching together relative schemes or relative modules. Relative schemes have this still ideal property that homomorphisms from one scheme into another, they just make a set, they don't make a category. But if you have a relative topoi, you see that the homomorphism from one into another, you can't escape it. They really form a category. And in an object and a morphism, I mean, it's really only defined up to canonical isomorphism. You never have real transitivities, etc. And if you want to glue together a topoi, you see, and this situation really does arise sometimes, well, you have a topos over s prime, and then you give not an isomorphism but an equivalence between the 2 inverse images on s second. And this here will not be an identity between composition of equivalences, but we will have an isomorphism between these compositions. And these isomorphisms should satisfy a transitivity relation when we go over to the fourfold fiber product. So you see that this situation suggests a good sequence of higher and higher order descent data. All right, but let's be satisfied that we don't need more than 2 descent. So this is a theorem, and we have then deduced from this some useful consequences. For instance, that if we have a submodule, if you have a submodule already on M, then we have an exact sequence which goes from the set of submodules of M to the set of submodules of M prime by double arrow to the set of submodules of M second, which is the descent of submodules. I have, by the way, thought over it whether you could get this from just using one descent in some way or other. I don't think so. It's really, you have to use the fact that you have a morphism of effective descent here. So that you have the descent of submodules and, of course, equivalently to the descent of quotient modules. And if you apply this to the case when M is equal to OS, this gives you the descent of closed subschemes, and from this one deduces the descent of arbitrary subschemes, at least if they are retrocompact. And the case of open subschemes is in fact more trivial. It just comes from the fact that topology of S is a topology of S prime, no more. And using these facts, we have seen that, as a corollary, that our morphism here, which is basically quasi-compact, is a morphism of one descent for schemes over schemes. So, which means, now I just repeat, you replace M and N by X and Y, relative schemes over S. That hom XY goes to hom X prime Y prime is injective. That would mean zero descent. That is that the factor of base change from schemes over S to schemes over S prime is faithful. The next step, we want a little more even, namely that for every X and Y over S, hom XY goes by one arrow to hom X prime Y prime, goes by 2 arrows to hom X second Y second. Should be an exact sequence. Name a homomorphism of schemes of the schemes X prime and Y prime over S prime descends, if and only if the two homomorphisms they define from X second to Y second are the same. So this can be expressed by saying that the inverse image factor viewed as being a functor from schemes over S to schemes over S prime endowed with descent data is fully faithful. And here, unfortunately, we can't go further. In fact, it's false. It's definitely false in the general case that this functor is an equivalence of categories. There are similar conditions of representability which have to be taken into account. But we will, however, give an important case where descent data are affected when we have an X prime over S prime, scheme over S prime, endowed with descent data relative to S prime goes to S, something like this, with transitivity condition here, as usual. I will give an important case where such descent data are effective, where there exists an S over S, giving rise to X prime with its descent data up to isomorphism. That's the case when X prime is an affine over S prime. So let's state another corollary of this main theorem here. The morphism considered is a morphism of two descent, or a morphism of effective descent, for schemes affine over other schemes. Affine over schemes. So we will show this as a corollary of this here. And for this, let's recall that the scheme affine over S corresponds just to a sheaf of algebras over S, let's say A, which is quasi-coherent as a sheaf of modules. Therefore, replacing the category of affine schemes over S and S prime, etc., by the opposite category of quasi-coherent algebras over S, S prime, etc., we are reduced to proving that G is a morphism of effective descent, for the finite category of quasi-coherent sheaves of algebras over variable schemes. But now, what is a quasi-coherent sheaf of algebras? It's a quasi-coherent sheaf of modules endowed with some extra structures. In fact, there's just one extra structure, A tensor A goes to A, the multiplication law, and which should satisfy a certain number of axioms. But, of course, our inverse image functors are compatible with tensor products that transform tensor products into tensor products up to isomorphism. And therefore, we see that if an algebra A over S, then to give a composition law on A, a bilinear composition law, is the same thing as to give a bilinear composition law on A prime compatible with the descent data. Because it means that we give a homomorphism from A prime tensor A prime into A prime that are compatible with the descent data, which just means that it comes from a homomorphism of A tensor A into A. So here you just use the fact that S prime goes to S is a morphism of one descent. And using the fact that it's a morphism of zero descent, we see that a certain composition on A is associative or commutative or unitary. Let's say associative or commutative, let's say, if and only if the composition law on A prime has the same property. Because we have to say that to check that some diagrams here are commutative. That some diagrams here are commutative, knowing that they become commutative after base change. And is here a faithful functor. It's all right. And using one descent, we see that if A prime has a unit element, a two-side unit element, then A has a two-side unit element, because this unit element, you see, can be viewed as being a homomorphism from OS prime into A prime, satisfying certain conditions. And because of unicity, it must be stable under descent data, this homomorphism from AS prime into A prime. Namely, the two unit elements that you want that you will get in S second by inverse images must be this, by the two inverse images must be the same in the two unit sections. Therefore, they come from a section here. All right. So, putting together all these things, we see that S prime goes to S because it is a morphism of one descent for quasi-coherent modules. Whenever it is a morphism of one descent for quasi-coherent modules, it will be also a morphism of one descent for quasi-coherent sheaves of algebras. And on the other hand, if it's a morphism of two descent for quasi-coherent modules, then we see in the same way that it must be a morphism of two descent for quasi-coherent sheaves of algebras. Now I mean by sheaves of algebras that are commutative, associative, and unitary. Because if you have a sheaf of algebras on S prime quasi-coherent, together with descent data, first of all it descends as a sheaf of modules, and then, by what we have said already, the algebra structure descends also. So this proves our corollary about effectivity. So let's go on in our list. Now let's again G be as before quasi-compact, quasi-separate. We have our morphism F here. Well, I mean it's a situation that I wrote down there. Over S, which gives rise to F prime over S prime. Then I say that F is affine if and only if F prime is. F is quasi-affine if and only if F prime is. F is integral if and only if F prime is. it's finite. You have not seen it yet, have you? No, I don't think so. Good. It's finite, and let's say quasi-finite, if and only if f prime is. So these were a few properties of morphisms which we have not been able so far to show that they are compatible with descent. So now we can do it. So the key case is this here. Of course, all the properties here are stable by base change. So all we have to prove is the implication from right to left. Now, of course, we can assume if we want that y equals s and y prime equals s prime as usual. Or we can forget about s prime and s and just look at this crazy compact faithfully flat morphism from y prime into y. So assume that x prime is affine over y prime. We want to prove that x is affine over y. And therefore we look at x prime over y prime. How should we say this? Endowed with its descent data. We know that viewed as being an affine relative scheme over y prime, these descent data are effective. Namely, we know that we can find a scheme x1 over y, affine over y, in such a way that its inverse image x prime 1 over y prime, together with its descent data, is isomorphic to x prime with its own descent data. Alright? But because this morphism is a morphism of one descent for all relative schemes, affine or not, if we have an isomorphism between the two inverse images of x and x1 compatible with descent data, this comes from an isomorphism between x1 and x. And therefore x1 being affine over y, x must be affine over y. Alright. I'm sorry, I couldn't erase it. Now, what about quasi-affine? What means that x over y is quasi-affine? That means, on the one hand, that it's coherent over y, and on the other hand, that if I look at the direct image by f of the structure sheaf of x, we now know because when we assume f to be coherent, we know that this A is a quasi-coherent sheaf of algebras. And if you look at the morphism which goes from x to the spectrum of A, then this morphism is an open immersion. That's what it means. That the morphism is quasi-affine. Now, assume that f prime has this property. That is, that x prime goes to the spectrum of A prime, where A prime is a direct image of the structure sheaf of x prime, is an open immersion. Alright, now first of all, f prime will be coherent, and therefore f will be coherent. The coherence descends. And therefore we know that the sheaf A prime on y prime is the inverse image by the base change from y to y prime of the sheaf A. This comes from the fact that taking direct images of quasi-coherent sheaves convolutes with flat base change, in the case that the morphism f is coherent. And therefore this morphism here is deduced from the morphism from x into the spectrum of A by just making the base change from y to y prime. So this is a morphism which becomes an open immersion after faithfully flat quasi-compact base extension. So it was an open immersion before. So that set us quasi-affine. What now about integral? Well, assume f prime to be an integral morphism. So it's affine, and therefore f is affine. So let's denote by A the sheaf of algebras that defines x over y, so that x prime is defined by A prime. So the assumption f prime now means that A prime is integral over y prime. And then it's an immediate corollary that A is integral over y. In terms of commutative algebra, this means the following. If we have a ring A and an algebra A prime over A, which is faithfully flat. And if you have an algebra B over A, and if B prime over A prime is integral, then this implies that B over A is integral. Now let's prove this. And of course the same with finite. If B prime over A prime is finite, then B over A is finite. So let's first prove the case finite. Well, finiteness is a property of the modules only, and we know what is that. The property for module to be of finite type descends. Now, what about integral? Let's write B as being the direct limit of the subalgebras of finite type Bi contained in A. Then it's known that B is integral if and only if the Bi's are finite over A. That's a property of being integral. Now B prime will be the direct limit of the B prime i's contained in B prime, where B prime I is deduced from Bi a base chain, and because A prime is flat over A, the B prime i's are really contained in B prime. All right. And because B prime is assumed to be integral, these B prime i's will be finite over A prime, and therefore Bi is finite over A by descent. So this.
We use these faithful flatness. You seem to have used them with flatness.
Well, I mean, to descend modules of finite types, we have to use faithful flatness. The property that the module of finite is a finite type, you see. So integral and affine is done here, and quasi finite, if we define it by just like quasi affine. What does quasi finite mean? Have you defined it, by the way?
Yes, you did define it.
Maybe we drop quasi finite. It's not too important. I think we define quasi finite as meaning it's the finite type and the fibers are finite. Now, of finite type it descends, and the fibers are finite. That's something that we look up over fields, and that's very clear that this descends too. So we use, in fact, for descending the property of the fibers, we just have to use the fact that S prime goes to S is certain. All right. So this has nothing to do really with affineness, although, but it kind of creeps naturally in the enumeration, because when one says finite, one thinks it is finite. All right. Now, I said that unfortunately projectivity of a morphism doesn't descend. However, there's something which is very much tied up with projectivity, namely ampleness. And for invertible sheaves, this is the property that descends. So let's give the statement. So we have the same property, the same situation as always. But now I give an invertible sheaf L on X, and I have the inverse image L prime on X prime. And I claim that L is ample with respect to F, or very ample with respect to F. So we have in fact two statements. If and only if L prime is ample or very ample in the respective case. With respect to F prime. So can we prove it with what we know so far? It seems so, yeah. So let's start with very ample. Let's look what this means. Of course, the property is a local one of being very ample, so we can assume y and y prime to be both affine if you want. So very ample means two things. That first, of course, as we know that these properties are stable under base change, we have to prove only that the right applies to the left. Now what does it mean that L is very ample? It means first that if you look at the inverse image of the direct image of L, mapped to L, that this is an epimorphism. It's a surjective homomorphism of scheme. And second, once we know that this is surjective, this, according by the universal property of the projective bundle associated to F star L, let's give a name to this, call this E. This is defined as a morphism from X into the projective bundle associated to this E. And the next is to state that this should be an immersion. So this is a universal way of mapping X by an immersion into a projective bundle in such a way that the sheaf induced by the canonical sheaf on here should be the sheaf L. So that's what very ample means. Plus, I'm afraid.
Have you used the reduction? Have you used the reduction to y affine?
Because if y is covered by affine open sets.
No, I mean these two conditions. To say that aren't these two conditions just very ampleness, or?
Yes, it's very ampleness.
You didn't use the reduction to y affine yet.
For the time being, no.
Yeah.
I wonder if I will use it at all, by the way. It was just to encourage you. Yes. Now, assume that that the assumptions of very ampleness is true here. So this will already imply that x prime is coherent over y prime, and therefore x is coherent over y by descent. And therefore, taking the direct image of L commutes with the flat base change here. So we know therefore that the sheaf E prime equals direct image by F prime of L prime is just reduced by inverse image from E. Alright. Now we know that the inverse image of E going to L maybe is not an epimorphism, but it becomes an epimorphism after we pass over to X prime. And because X prime over X is faithfully flat, it was an epimorphism before. So the property A descends in an evident way. You just have to use the fact that forming the direct image here is compatible with base change. And now, once we know this, it's clear again that the morphism which goes from X prime into P of E prime is reduced from the analogous morphism from X into P of E by base change. Now this morphism from X into PE is certainly quasi-compact because PE is separated over Y and X is coherent over Y, and therefore it's quasi-compact over Y. So we have a quasi-compact morphism. It becomes an immersion after our base change of quasi-compact, faithfully flat base change. So it was an immersion before. And that does it for very ample. Now, what about ampleness? Ample means the following, that whenever F is a sheaf quasi-coherent of finite type over X, for every F quasi-coherent of finite type, there exists an N. At least that's the definition if we assume Y to be quasi-compact. So here we have to make a little reduction. So we reduce to Y quasi-compact. There exists an integer N such that f of n is generated by its section relative to y, which means that the inverse image of the direct image of f of n mapped by the canonical adjunction morphism to f of n should be a p. That's what it means. And we have to prove that if such a property is satisfied after making our wave extension, then it was true before. Now assume the property is true here. This implies, I don't remember, we will say that L is empty, ample if this is true, and moreover F is coherent, something like this. Maybe we have to use it. Maybe we have to assume it beforehand. So F prime will be coherent, and therefore F is coherent. And therefore, taking the direct image of f of n commutes with space change. Now there exists an n such that f prime of n gets mapped epimorphically to it, f prime star of f prime lower star of f prime of n. Now this morphism with primes is reduced from the morphism here without prime by just making the base change. And so it becomes an epimorphism after making faithfully flat base change. It wasn't epimorphism before. All right. So I think that this gives a good sample of properties. There's properties that descend well, properties of morphisms, sheaves, etc. But now let's come back to the Sattler condition of effectivity questions for descent data. Now this is kind of a delicate matter. So the question is the following: we have a morphism S prime goes to S, which is as usual faithfully flat and quasi-compact. And I have an X prime over S prime, which is endowed with descent data. And so this means also, if you want, that the two inverse images of X prime over S second have been identified to one and the same X second. And the two projections of this to X prime can be identified with projections of X second to X prime lying over these respective projections. Here you have P1 and P2, and over P1 you have Q1, and over P2 you have Q2. In fact, it's easy to see that the condition that's something purely categorical again, categorical nonsense. That's a condition that's the gluing data is in fact a descent condition, namely that a certain transitivity condition holds over S third, just means that this double arrow lying over the double arrow P1, P2 turns X second into an equivalence relation X prime. So the transitivity condition here is just the transitivity condition for an equivalence relation. And
could you say it again, please?
That whenever you have gluing data on X prime over S prime with respect to S prime over S, you have an isomorphism between the two inverse images of X prime over S second. Then identifying X second 1 and X second 2 to X second to a same scheme, let's call it X second over S second, where this isomorphism, we get two morphisms of this scheme X second into X prime, lying respectively over P1 and P2. So that's the two squares obtained from this diagram by taking P1 and Q1 here, or the other square by taking P2 and Q2 here, are commutative. And not only commutative, but in fact Cartesian. Alright? Now, this you can do whenever you have gluing data. Now, when we have a double arrow like this, it makes a sense to say that this double arrow turns X second into an equivalence relation X prime. That means that for every testing object of the category Z, of the category we are working with, the category of schemes, if you look at X second Z mapped by a double arrow into X prime Z, or what amounts to the same, mapped by a single arrow into X prime Z times X prime Z, that X second Z becomes the graph of an equivalence relation, so that X second Z going into this product set is injective, and it becomes an equivalence relation in X prime Z. But I can try already to explain what these kind of things mean. I think I did it at least in the course on February. All right. And all right, now what I say, and it's general nonsense verification, it has nothing to do with schemes even, it's that our doing data are in fact descent data if and only if this double arrow turns x second into an equivalence relation in x prime. And you will remark that in this equivalence relation, Q1 and Q2, the two projector morphisms, have the same property as S prime goes to S below, because they are deduced from P1 and P2, which are deduced by base chain from S prime goes to S. You see, it's S second is just a fiber product of S prime by itself.
Which equivalence relation is this?
Well, I mean, look at, assume that everything is sets, you see. It's the equivalence relation such that the quotient that we are looking, if there was a quotient, would be X, you see. If S prime, etc., if you're working in the case of sets, or if you want to stay still in schemes, take schemes over a field, let's say, but take constant schemes. So the category of these schemes is just equal to the category of sets. And assume that X prime is a set lying over S prime, or constant scheme. Over on every fiber, you see. Fiber-wise, it's constant. It's a set lying over S prime, endowed with a descent data for S prime goes to S. Right now, in the category of sets, you see, it's quite easy to see that every surjective map of sets is a morphism of two descent, in fact. For sets relative, for red sets over others, it's kind of trivial. And so in this case, we can construct the descended set X, and what you see is that it's just the quotient of X prime by the equivalence relation. So this equivalence relation X second is just the fiber product of X prime by itself over X. So what we're looking for is the possibility to complete this diagram, you see, in such a way that X prime goes to X should have the same property as prime goes to S, then we phase compact, in such a way that she should be able to recover X second as the fiber product of X prime by itself over X. In fact, what can be shown, and that's again general nonsense. I don't want to dive too much into proofs of general nonsense statements, you see, because it may take us months if you really wanted to do it. I mean, with all details, you see, and being very careful. Or else it would take months to prepare it and to make an exposition in a few hours. But anyhow, we don't have time for this. So that the descent condition is effective if and only if the quotient of X prime by this equivalence relation, now how would I say, exists and is effective, namely that we recover the equivalence relation X second as being the fiber product of X prime by itself over X. So how should I? So what is the general nonsense statement? Let's at least give the statement. Assume that we are in a certain category. It may be the category of schemes, it may be another category. And assume we have a morphism S prime goes to S, which is a morphism of one descent, not effective descent, just of one descent, for the fibered category of relative objects over S prime, etc. We assume that in this category fibered products exist, so that we have the fibered category of objects over others. When we have an object X over S, then for every morphism from an S prime into an S, we can define an object X prime over S prime, which is the inverse image of this by taking fibered products. Alright. And therefore, having a fibered category over a category, it makes sense to say that the morphism is of 0, of 1, or of 2 descent with respect to this fibered category. So assume that we have a morphism S prime goes to S, which is of 1 descent for this particular fibered category. Of relative schemes it would be here. Alright. Now take an object X prime over S prime together with descent data. So descent data now, what I said, you can interpret it as being just an equivalence relation X prime lying over the equivalence relation S second in S prime defined by this morphism where S second is just a fibered product. So that you have in such a way that you have two Cartesian squares here, not only two commutative squares, but two Cartesian squares, so that the x second is the inverse image of x prime of s prime by either of these two arrows. All right. So that's the descent. That's the way of expressing descent conditions. And I claim that the descent condition is effective if and only if this equivalence relation is effective. In other words, if and only if the quotient exists, and within the category, in the naive sense, and moreover, the equivalence relation x second can be reconstructed from this morphism from x prime to its quotient as being the fiber product. So being a general nonsense statement, I will admit it. It has nothing special to do with schemes, you see, rings and ring spaces, etc. It's just categories. So this gives a relation between question of passage to quotient and question of effectivity of descent data.
Don't I think that quotient, let's see if I got automatically in this universality of that quotient is universal effective. Not at the square involving x is Cartesian too.
You think that the statement may be false?
Well, I think it needs just one additional statement that the arrow from x prime into x that you require. If that equivalence relation
be universal.
Yeah. I need that.
Okay.
I need that. Otherwise, that square isn't necessarily Cartesian.
Yeah, I think you are right. Yes. Yeah. So I think I made a slight misstatement. You should. You should state not only that x second is an effective equivalence relation, but effective and universal. Namely, that this quotient should remain a quotient after we make any base change. If you have an x1 goes to x, and if you take that's the inverse image of x prime over x1, so we call it x prime 1, then x1 should be the quotient of x prime 1 by the consolidation deduced from x second by base change. Yeah. Now let's give a kind of tautological necessary and sufficient condition for effectivity of descent data in the case when we're working with schemes now. And when s prime goes to s is assumed to be of one descent, that's enough. For instance, it's assumed to be faithfully fed and quasi compact.
Excuse me, the bottom arrows to begin with,
Yeah.
isn't S already a quotient, universal quotient?
Of s prime, yes.
Isn't it?
Yes. Because we can prove the following also.
So,
that a morphism, you see, a morphism in a category where private products exist is of one descent for the previous private category, if and only if it's an effective universal epimorphism. That means it's an epimorphism, but it's an effective epimorphism, namely S is a quotient of S prime by this double arrow. And third, it remains an epimorphism, an effective epimorphism, after any base change.
I mean, if the bottom arrow is universal in this sense,
Yes.
shouldn't it follow the second is too? Because in the third,
No, yeah, if and only if this square is Cartesian, you see. But what is not clear is that once you make the pass to the quotient, of course, this quotient will be mapped to S because we have a morphism from x prime into S, which equalizes these two arrows. Because to take this compositum is the same thing as to take this compositum, and these two arrows are equalized by this one. And therefore, this morphism factors through morphism from x into S. So certainly you get a canonical morphism of the quotient into S, but what is not clear, as Jack pointed out, is that this diagram should be Cartesian. So it's the same thing to say that the quotient is universal effective, yes, or to say that this diagram is Cartesian. But I like to give a statement, you see, which makes no longer any reference to the bottom line. So which is just a statement about an equivalence relation. And so I want to that this equivalence relation should be effective universal. Namely that the quotient exists, that the equivalence relation is reconstructed from for the morphism to the quotient, and that this situation should be universal with respect to base changes over X. So then that's a property, purely intrinsic property to the cancellation, where we can completely forget about the bottom line. And now let's give a tautological statement in the case, more or less tautological, in the case when you're talking in the case of schemes, where we have a notion of open coverings and where we have a notion of being able to glue together schemes by open pieces. So, of course, when we have an object x prime by s prime endowed with descent data, it makes an obvious sense if you have a sub-object x prime I, let's say, of x prime, it makes an obvious sense to say that x prime I is stable under the descent data. In terms of this diagram, it just means that the two inverse images of x prime I in x second by q1 and q2 are the same as sub-objects, of course, not just as subsets. Sub-object is a scheme, and now it is an arrow into x prime. It is a monomorphism. So, I mean, this notion of stability under descent data makes an obvious sense again in any category. But now, let's look at, in the case of scatter of schemes, let's look at open subsets of x prime, viewed as being open subschemes, namely endowed with the induced structure, that are stable under the descent conditions. In fact, this condition is purely set theoretical. It just means that the two inverse images of the subscheme in x second are the same, but these inverse images are open subschemes. To say that they are the same just means that they are the same subsets. Alright. Of course, also the fact that the subset is stable under Dickin's condition relation makes a sense. It means that the inverse images of this subset in x second by q1 and q2 are the same. So for open subschemes, it means one to the same to say that the open subscheme is stable or that the corresponding subset is stable. Alright. Now assume that x prime is the union of such stable open subsets. Now if we have, of course, if we have a sub-object x prime I, whether open subscheme or not, which is stable, then the inverse image, the unique inverse image of x prime I in x second by the two arrows defines you an x double arrow from x second I into x prime I, which again is a descent condition, because it's an induced equivalence relation. And of course, the diagrams which we have over, which you get over s prime double, s second double arrow s prime are Cartesian by transitivity. So you have the induced descent data. All right. And now assume, the statement is the following: for the descent data here to be effective, it's necessary and sufficient that for each of the x prime i's, the induced descent data should be effective. And let's prove this. First, let's assume x prime, the descent data on x prime are effective. So there is an x over s, which gives rise to the whole bunch of things. And by the way, it's a statement about equivalence relations s to n, but never mind, you can do it either way. As a statement about descent conditions or about equivalence relations. Now, x prime I is an open subset of x prime, which is stable under the descending conditions here. That means that the two inverse images on x second, which now can be interpreted as being the private product of x prime by itself over x, are the same. But by what we have seen, this implies that it comes from an open subset xi of x. Alright? And because the x prime i's cover x prime, the xi's, what did we want to prove? No, we want to prove that the induced, that's it. And of course, xi will be the quotient of x prime I by x second I, because x second I is just the private product of x prime I by itself over xi. And this here is faithfully flat, crazy compact, because it's reduced from this by base change. So this in one direction is trivial. Now let's look at the other direction. Assume that the equivalence relations, that the descent data here are effective. In other words, that the equivalence relation is effective universal. So we get schemes xi over s and we have to prove that the equivalence relation in X prime is effective universal, or that the descent data is effective. And we do this by gluing together, we construct the X over S by gluing together the Xi's. And I mean, the idea is pretty obvious. The X prime I's, and if you look at the intersection of X prime I with X prime J for two indices I and J, this again is stable on descent data, and therefore it descends to an Xi J, if you want. And of course, you will now be able to glue together the Xi's according to Xij. So I could spend now 50 minutes trying to make it explicit, but I think it's not worth it. I mean, anybody can write down a proof. In fact, you could also directly define a functor. You see, whenever you have an equivalence relation, let me give an alternate way of doing this thing in order to reduce to a statement which is already known. Assume that we have an equivalence relation in some object. Call it Z, this would be X prime. An equivalence relation R, where we assume that the morphisms P1 and P2 are faithfully flat quasi-compact. What is really important is that there should be morphisms, effective universal epimorphisms. There should be morphisms of one descent in the category we're working in. Again, what I'm going to say is, in fact, general nonsense about categories. All right. And we wonder if this equivalence relation is effective universal, if there exists an effective universal quotient X. And now, if there is one, let's directly describe the functor that it represents. And whenever the quotient exists, and then the statement will be that the quotient exists if and only if the functor that has a meaning independently of the existence of this quotient anyhow, if and only if this functor is representable. Now let's describe the functor. So for every t, I have to describe in terms of this here, what are the morphisms of t and x. All right, but let's rather call it, yes, let's rather call the variable object x1 just by putting a subscript to x. All right, if we have a morphism from x1 into x, then we deduce by base change from this situation, by base change by x1 goes to x, we deduce a diagram z1 and z1 times over x1 z1, which is equal to r1. Let's yeah, so that's all right. Never mind, that's just the finite product. As R is the finite product of z by itself over x, the inverse image of r by x1 goes to x, and that morphism will be just the finite product of z1 by itself over x1. And then if you have arrows like this, you will get such a diagram. And now in this diagram, forget about x. We see that whenever we have morphisms from x1 into x, we get a diagram as follows. We get a morphism from z1 into x1, which will be a morphism of one descent, let's say. If this morphism was faithfully flat quasi-compact, for instance, then we would even say that this morphism would be faithfully flat quasi-compact. We have some leeway in the way of expressing things. So we know what the quasi-compact faithfully flat morphisms are, but whereas we don't know really what the morphisms of one descent are so well. So sometimes it will be easier to make this. Yeah?
As you forget x, how you describe the z1 and...
No, I want to describe a functor in terms of this. Of course, in order to define the homomorphism of the functor presented by x into this functor, I have to use the x. You see, I mean, I say what... I will say the following. I'm going to define a functor with respect to variable x1, define using just this here. And the objects of this functor are the following things. So call this functor phi if you want. Phi of x1 are isomorphism classes of following objects. in fact, the category I'm going to describe, in which I'm going to take isomorphism classes, it's a rigid category. There are no automorphisms, except identities. So therefore taking isomorphism classes is not a unpleasant thing. So these are isomorphism classes of following objects. We have a morphism Z1 to X1, which is of one descent, or let's say face-to-face quasi compact. If this one was, if P1 and P2 were face-to-face quasi compact, plus a morphism of Z1 into Z and of this fiber product into R, so that the two squares deduced by taking P1 and Q1 here, or P2 and Q2 here, should be Cartesian. That just means that this morphism from Z1, that the equivalence relation Z1 times XZ1 and Z1 is the inverse image by this morphism of the equivalence relation we have here. That's what it means. All right. And you look at isomorphism classes of such things for a given X1, and they form a set, and this set quite evidently depends on the constant plane of X1. Whenever you have an X2, let's say, mapped into X1, and if you have an object like this over this here, then you deduce by inverse image an object over X2 by just taking Z2, the higher product. You see, and by just composing. Alright, now what I claim is that when this quotient X exists in a universal, effective universal way, then you have a natural map which goes from the functor represented by X, which I identify to X, or let's call it X tilde perhaps rather, to this functor phi. Namely, for every morphism of X1 into X, you have such a limit of phi of X1. And this, of course, is compatible with inverse images. And what I claim is that this canonical map is an isomorphism. And now, so we see that the necessary condition for this equivalence relation to be effective universal is that the functor phi that is described in terms of this equivalence relation should be representable. All right, and now the converse holds. If the functor is representable, then the object that represents it must be an effective universal quotient. It's just an exercise. Let's start the proof if you want. Assume that it's representable. So we have a universal element in some phi of X, call it X, the object that represents it. So we have how should I say? I hope. What I want to prove, that's it. I have such a diagram which is universal. What I want to prove, I guess, is that this is an isomorphism. And therefore this is an isomorphism. Of course, when I prove this, then in fact the X can be put in here, and all we then have to prove is that X is an effective universal quotient. So I think we will admit this point. I'm pretty sure not only it's true that even there are references somewhere in the seminar of de Mazure or the seminar of Grothendieck. These things have been written up. And this is general nonsense, you see. And therefore, the problem of effectivity of descent data, or what amounts to the same, or generalizing the problem of effectivity and universality of an equivalence relation in an object, boils down to a still more general question, namely the question of seeing whether a certain functor is representable. And the functor is in fact the quotient, is what we should call the quotient, is a category of, well, sheaves in fact. So this point of view of embedding objects in sheaves we will speak more about tomorrow. But now let's come down to the situation which we have here. What we will see is that if x prime is covered by open x prime i's, then the functor that is represented by this situation here, we call this functor x after all, you see. We don't know yet if x is representable. But this functor x will be covered by subfunctors xi. In fact, this functor will be a sheaf. Yeah, it will be a sheaf for the Zariski topology in the sense we have explained months or so ago. That's pretty obvious by the very description of which we gave of the functor. So the sheaf x, if x prime is covered by the open subset x prime I, then x will be covered by the subfunctors xi, and they will turn out to be open subfunctors. And then, according to the general representability criterion of a sheaf by a scheme, the sheaf x will be representable if and only if the xi's are representable. Maybe if and only if the equivalence relations that we have in the x prime i's that are induced by the one we have in x prime are effective. You see, if we wanted to really carry through the starting of the proof I gave of this relative effectiveness criterion, if the induced descent data are effective on the x prime i's, then the descent data on x prime is effective. If we wanted to carry through directly the proof, all right, now let's give some corollaries of this general nonsense remark. Yeah, assume that we can cover x prime by open subsets x prime I that are stable by this descent data, and moreover, such that these x prime I over s prime are affine. For instance, that s prime s is affine itself, this would just mean that x prime i's are affine themselves. Then the descent condition, then the descent data on x prime are effective. Because we know already that on a scheme that is affine over s prime, any descent data are effective. I assume now s prime over s to be facially flat and quasi-compact. So, yeah. In fact, if S is affine itself, then we can say that a necessary and sufficient condition for descent data on x prime to be effective is that we can cover x prime by open subsets x prime I that are affine over s prime, and such that the induced descent data should be effective. So we have seen it's sufficient, let's prove it's necessary. Because if x prime over s prime comes from an x over s being affine, if we cover x by affine open sets xi, these affine open sets must be affine over s. and the inverse images in x prime I and x prime will be affine over S prime. And of course the induced descent data must be effective. So in a way, we have a necessary and sufficient condition, but it's kind of tautological, you see. In many cases it will be quite hard directly to construct open subsets x prime I and x prime that are affine or affine over S prime, let's say, and which are stable under descent conditions. So that's really the main difficulty. We have just kind of pointed out, in different terms, where the real difficulty lies. It's to construct these open subsets. Now, let's give, however, a few cases. Let's list a few cases where this condition can be checked, and therefore where we have effectivity of descent conditions, of descent data. First, assume that our morphism G, which is faithfully flat and quasi-compact as usual, assume it's moreover Radischer. So it's injective and universally so. Therefore, S prime goes to S, in fact, is a universal homeomorphism. Remember that the topology of S is the total topology of the one as S prime. On the other hand, the morphism of G is injective, being Radischer. So it's therefore bijective. And the topology being a total topology, that means it's a homeomorphism. And this, it remains, of course, a homeomorphism by any base change. So all assumptions are stable under base change. All right. Now, let's look at a scheme x prime over S prime endowed with descent data. I claim now that any open subset, whatever, is stable under the descent data. Why is this? All right, let's look what it means. We have x second over S second with the two arrows into x prime by q1 and q2. And to say that a subset of x prime, I say any subset, in fact, whatever, also is stable under the descent data. Of course, to say that an open subscheme is stable means that the subset is stable. Why is any subset stable under descent data? It just means that the two inverse images of q prime by q1 and q2 are the same. But I claim that q1 and q2 sets theoretically are the same maps. In fact, they are bijective. This comes from the fact that S second goes to S prime, you see, is set theoretically, they are set theoretically the same maps. But that's not a good reason. But let's say the following. It's because if I look at, yes, let's say it's the following way. These two morphisms can be viewed as being reduced from the diagonal morphism from x second into its finite product over x prime by composing with the two projections of this on x. It's a mere triviality, but why is it true? Let's see, how will I say this? Now this map is bijective. That's I mean, of course, because the morphism the x prime goes. I'm sorry, there's something. No, I don't have a finite product here because I have no. Let's see. There are two arrows in fact. How should I say these things? Let's say this following thing. Let's look at the diagonal morphism here. S prime goes to S second. Then this diagonal morphism is bijective. It's injective, of course, always, and on the other hand, it's surjective. That means that S prime goes S is Radischer. So you have a bijective morphism, bijective map, and when you compose it with these two arrows, it becomes identity. That means that these two arrows are the same set theoretically. Of course, these arrows are bijective too. And now why is the same true? Let's see. Now let's look at the inverse image of this morphism, of this diagonal morphism. Then we get a Cartesian square, call it x1 goes to x second, in such a way that the compositum of these two arrows with this one here are the same. That's it. But this map here is bijective too, because this here is universally bijective. Alright. And therefore set theoretically Q1 and Q2 are the same. Is it clear? Q1 and Q2, they're different as morphism of schemes, but for the underlying sets they are the same. It's on the sheet of things that are different. But they may be different. So I mean, it's just a triviality. I just got kind of mixed up. If you set it in terms of geometric points, I think it would be still clearer. Because, but never mind this. All right, and therefore, if you have any subset here, it's two inverse images by Q1 and Q2. I mean, they are the same because Q1 and Q2 are symmetrically identical. So any subset of X prime is stable under descent data. All right, now in order to prove effectivity, I can reduce to the case when S and S prime are both affine. That's it. It's just clear that we can reduce to the case that S prime is affine. All right, let's do it. We have already shown how we can reduce to the case that S is affine. The effectivity question is local on S. Now what about S prime? All right, assume S affine, and I think we have done something like this already, slightly different context. Assume that S prime will now be quasi-compact. It can be covered by a finite number of affines. Take the disjoint sum of these affines. Call it S prime bar. Now S prime bar is affine and it's supposed to be flat quasi-compact over S. On the other hand, we have an S morphism from S prime bar into S prime. And now what I claim is that if we have scheme over S prime with descent data, in order for the scheme, for these descent data to be effective, it's less than sufficient that it becomes effective over S prime bar. It's exactly the same proof as in the case when S prime bar was a disjoint union of open subsets of S. You see, it comes from the fact that we, well, it's when some new diagram shading. This is again some general nonsense. All right, so let's assume S and S prime both to be affine. And then cover X prime by affine open subsets, X prime I. They are stable by the descent data, because any open subscheme is stable by descent data. And therefore the descent data on X prime is effective. The X prime I is being affine. So that's a purely inseparable descent. For instance, if you have a ground field K, and if you take a purely inseparable extension K prime, then for every scheme X prime over K prime endowed with descent data with respect to K, these must be effective. However, if you take a field extension that is not pure inseparable, we can find field extensions of order which are lower, of degree 2 for instance, and the scheme X prime over K prime, which is proper and even smooth over K prime. A beautiful scheme over K prime, but not projective, however. Such that together with descent data to K, which are not effective. So even for very special types of faithfully flat morphisms, like nice coverings of étale coverings of degree 2, you see, descent data may not be effective. Now let's give another condition of effectivity of descent data. Assume that we have a descent datum not only x prime, but on a pair x prime L prime, where L prime is an invertible sheaf on x prime that is ample with respect to s prime. L prime ample with respect to s prime. So that means that not only do we have this diagram with an x second here and with two Cartesian squares, but that the descent condition extends to L prime, that we have an isomorphism between the two inverse images of L prime on x second, satisfying a transitivity relation when we look at x third here. Then I claim that the descent data are effective. But I'm afraid that we don't have the prerequisites here for proving it, because I will give the principle of the proof, but it involves some technical development which we have not done here. I guess. Well, maybe I can do it in some cases at least. Yeah, let's try to give a proof. Yes, let's give a proof in the case when we know that there's a power of L prime which is very ample. So this would be, so assume in fact that there exists a very ample sheaf over S prime, stable under together with descent data on this sheaf. In this case, I think I can give the proof. Of course, if there's an ample one, there in most cases there will be a very ample one. This will be true, provided x prime is of finite type over s prime, which is not a very serious restriction, I guess, for most practical purposes. So I assume there's a very ample sheaf on x prime, and that the descent data have been extended to this sheaf. And that proves that things are right. Now, what does it mean that it's very ample? It means, I recall, that on the one hand, let's call f prime this morphism here. That f prime star of L prime, that its inverse image is mapped surjectively by an epimorphism to L prime. This allows us to define a morphism on x prime, this sheaf here on s prime. We call it E prime if you want. It's a quasi-coherent sheaf. And now, knowing that this is an epimorphism, this allows us to define x prime goes to P of E prime, call it I prime if you want, and the second condition is that I prime is an immersion. Alright, so these are assumptions of very ampleness. Now let's see. I claim that this sheaf E prime equals direct image of L prime, which is a quasi-coherent sheaf on S prime. It's quasi-coherent because F prime is coherent. And the image of a quasi-coherent sheaf by a coherent morphism is quasi-coherent. So we have a sheaf E prime on S prime. I claim that it's endowed with descent conditions with respect to S. In other words, I claim that the two inverse images E second 1 and E second 2 of E prime on S second are canonically isomorphic, and that this isomorphism satisfies a transitivity relation on S third. Now, why this? Well, you see, what are these two inverse images? Let's look at the inverse image by P1 first, and then by P2. All right. Taking inverse images by flat morphisms of direct images of sheaves is the same thing as taking the direct image by the corresponding morphism here of the inverse image. But here we have to take the inverse image by Q1. So let's look at L second 1. Therefore, this inverse image is L second 1. Therefore, this inverse image of E prime by P1 and the S second 1 is just the direct image of L second 1. And in the same way, E second 2 is the direct image of L second 2. And as we have an isomorphism here, we get an isomorphism there. On the other hand, the diagram that we get from the slewing data on S third by the same argument will be just the direct image by F third, which goes from X third to S third, of the corresponding diagram which we have between L third 1, L third 2, and L third 3. And therefore, this being transitive, this here must be transitive. Alright, so we have a descent condition on E prime. Therefore, we have a quasi-covariant sheaf E over S, because we know that the morphism G is a morphism of effective descent, a morphism of 2 descent for quasi-covariant sheaves. Alright. Therefore, we now can view E prime as being the inverse image of a sheaf E on S. And therefore, now let's look at P of E, the projective bundle over S associated to E. Call this just P if you want. So P of E prime can be identified to P prime, the inverse image, by the base shift S prime goes to S of P. And as this is an inversion, we can identify X prime to a subscheme of P prime. In fact, it's retro-compact subscheme because X prime is coherent over S prime. And now it's of course clear again always by the same types of arguments, that this subscheme of X prime is stable by the descent data. Because it has been constructed intrinsically, you see, in terms of the invertible sheaf L prime on X prime. And therefore, this subscheme, and in fact what is clear is that the morphism which goes from X prime into P prime is compatible with descent data which we have on X prime, because X prime was given at the very start with descent data. And P prime has descent data because E prime has descent data, or also because it comes from P, which are the same. Alright, so this is a morphism which is compatible with descent data, which is, again, you just look, quite evident. And therefore, the subscheme descends, because we know that we can descend subschemes that are retro-compact. It comes from a subscheme of P, which we call X. And of course, this X does it. So, and at the same time, of course, now, as that we have descended X prime to X, now this very ample sheaf on X prime appears as being a sheaf on X prime endowed with descent data with respect to X prime over X. And because X prime goes to X is of effective descent for quasi-covariant sheaves, because it's basically flat and quasi-compact. This L prime comes from an invertible sheaf L on X. It descends too. And because after base change this becomes very ample on S prime, this sheaf was very ample on S. So what we have seen is in fact the following thing. Call it a term if you want. If G is faithfully flat and quasi-compact, then G is an morphism of 2 descent for pairs for fiber category of pairs X prime, L prime over S prime, where variable S prime, where S prime is a variable scheme, X prime is a scheme over S prime, and L prime is an invertible scheme on X prime, which is very ample with respect to S prime. So that's really what we have proved. So not only effectivity of descent criteria on the scheme, but at the same time on the invertible sheaf, and with conservation of the property of being very ample. And now let's sketch an important application of this, which is one of the very useful criteria of effectivity of descent. So corollary, assume that G S prime goes to S is faithfully flat, finite, and locally free. So that just means that S prime can be viewed as being the spectrum of an algebra A prime over A, which as a sheaf of modules is locally free of finite type. Now being locally free already implies that A prime is flat over A. And everywhere, and of rank nowhere 0, of rank, this will take care of faithfully flat. Of rank everywhere different from 0. So that's what it means. And then X prime over S prime be endowed with descent data relative to S prime goes to S. And I assume moreover that X prime over S prime is, say, quasi-projective. More generally, it would be enough, I think, to assume that there exists an invertible sheaf L prime on X prime ample with respect to S prime. But if the morphisms of finite types, then the two assumptions are the same. Right? I claim then that X prime descends, that there exists, that the to an X over S, namely that the descent data are effective, and X over S is quasi-projective. So quasi-projective schemes can be ascended by faithfully flat morphisms that are finite at of finite type, that are finite locally free. Now I will just indicate the principle of the proof. One has to make slightly algebraic work in order to carry it through. According to what we have said, everything boils down to finding an invertible sheaf L prime on X prime, which is very ample with respect to S prime, and such that the descent data on X prime extend to descent data on L prime. That's really the point. Of course, if there exists a solution X over S which is quasi-projective over S, then taking an invertible sheaf N on X, which is ample with respect to S, or very ample with respect to S, then its inverse image will satisfy these conditions. So certainly I will have to find an L prime if I want that the theorem is be true. So the problem is how to find this L prime, and there of course I have to use the finiteness of S prime over S, which implies of course that S second is finite over S prime by either P1 or P2 and locally free. Now, also it implies that x prime by either q1, x second by either q1 or q2 is finite and locally free over x prime. And now the little astuce, the little trick in order to get this L prime is the following. I start with an m prime which is ample with respect to s prime. But for the time being there are no descent data on m prime. And I take its inverse image on q second by q1. I now look at its inverse image q1 upper star of m prime. I now get an invertible sheaf on x second, which will be ample with respect to s second. And I project it back by q2. I take q, but I take the norm with respect to q2. There's a certain operation of taking the norm of an invertible sheaf with respect to a morphism which is finite, locally free, which is tied up with the notion of a norm in algebra, which is free of finite type. So I have no time here to develop the notion of a norm. It's a pretty easy algebraic notion. So I take the norm with respect to q2 of q1 star m prime. And in fact, this is a very close, this is an operation which is taking first inverse image and then the norm by one of the projections, then the norm by the other. It's an operation which is very close to saturating a subset of x prime by the equivalence relation x second, which consists by taking first the inverse image by q1 and then the direct image by q2. That's a saturation. So here we have something like a saturation, because if we want to work entirely in the category of locally free sheaves of rank 1, of invertible sheaves, the notion of direct image is replaced by the notion of a norm. And that's the intuition of the situation. And in a way, the analogy can be carried through, for instance, by saying that if you have a section of m prime, you take its inverse image, which is a section of this, and then we take the norm of this section, which is a section of this, then the set of the open sets defined by the sections is, let's say, no, the set of zeros of the section which we have here, when we saturate this, is a set of zeros of the new section which we get for the new sheaf L prime. You see, so when we take sets of zeros of sections, then the operations which we have done on the invertible sheaves correspond to saturation operation on the sets of zeros. All right, and now when I said that L prime is kind of the saturation of M prime, this in fact means that now it has canonical descent data. Just as when you saturate a set, now it's stable under the descent data.
So norm q1 and q2 upper star M prime is isomorphic.
Yes. It comes from, that's a very easy algebraic play, you see. It comes from the fact that forming norms is compatible with space change, and you play around a little bit. And
is it very hard to define that?
the norm?
Yeah.
No, I will give you the definition, you see. You have a situation T prime over T. T prime is the spectrum of an algebra B over OT, and the algebra B is supposed to be locally free of finite time. And now you have the norm, first of all, a norm which goes from B to OT, which is well known, you see. For a section of B, we take the left multiplication by the section as an endomorphism of B, and we take the determinant of this endomorphism. So we get a homomorphism delta, let's say, or norm, let's say, that's it, norm of B over OT, which has the property of being multiplicative. Norm of xy is equal to norm of x, norm of y, and which transforms 1 into 1. It's of course not additive. All right? And therefore it transforms B star into OT star. It transforms the invertible sections, the sheaf of invertible sections here, into the sheaf of invertible sections. And therefore, whenever we have a torsor under B star, we can take the associated torsor through the homomorphism, which will be a torsor under OT star. So whenever we have now to give a torus under B star, it's the same thing as to give a sheaf of modules over B, which is locally free of rank 1. Now a sheaf of modules over B is the same thing as a sheaf of modules over 2. I was saying crazy coherent, I'm sorry. Yeah. It's the same thing as a crazy coherent sheaf of modules over T prime. And to say that the sheaf of modules over B is invertible means that the sheaf of modules that we have over T prime is invertible. And so we have now a way of associating to an invertible sheaf on T prime, while a torus on a OT star, which is the same thing as invertible sheaf on T. So it's just associated, this is associated by passing two toruses to the usual norm homomorphism between algebras. And it's stable with base change. I mean, it has all nice properties. There's nice properties of transitivity too. But I don't think we have to use this. I think everything comes formally out of the fact that it's stable under base change. The fact that this L prime has now descent data. And on the other hand, it's quite easy to see. So this works for any invertible sheaf M prime on X prime. We can saturate it in a certain way. And on the other hand, it's easy to see that ampleness is stable both under taking norms and taking inverse images. I mean, inverse images, we know that it's stable, but also that it's stable under taking norms. And so that's about it. I think we have to stop. So tomorrow I will give a few more corollaries of these results, and then we will try to put this notion of descent into a certain perspective and connect it with a point of view of generalized sheaves and explain in general terms how for instance, the passage to quotient by more or less general arbitrary constellations can be best dealt with in the context of generalized sheaves. So I won't be, I'm afraid, too precise and basic tomorrow. I just try to pass through some yoga. With a scheme which is proper and smooth of dimension 3 over the extension field K prime with descent data which don't descend, which are defective. So the situation is kind of delicate. Let's give another application. Let X be a scheme over K. Let's say, well, the right side of state N. Let's start with a scheme over K and assume that after base extension to some other ground field K prime, that X prime is quasi-projective or projective, say. Then I claim that X is quasi-projective or projective. You recall that under marginal conditions, it's not true that quasi-projectivity or projectivity descends. But if you have a field extension, it does. And we will see how. Of course, the projective case is a particular case of quasi-projective because we know that properties have sense. So it's really quasi-projectivity, which is interesting. All right, K prime is the Dieck limit of subalgebras of finite type AI, and therefore X prime can be viewed as being the inverse limit of what we deduce from X by making the extension from base extension from K to the spectrum of AI. And I mean, as practically all geometrical notions that we have introduced so far, I mean, the notion of being quasi-projective passes to the limit. I mean, it's pretty clear because if you have an invertible sheaf L prime on X prime, you see, which is ample with respect to K prime, then for I big enough, it comes from an invertible sheaf L prime Li over Xi. I mean, that's the general the general story which we had explained at length. And now we have to show that if L prime is ample, Li must be ample, provided we take I beginner, right? Maybe we make still another extension. But this comes from the fact that the notions that come in defining ampleness, maybe that a certain homomorphism of shield is epimorphism. I mean, these notions pass well to the limit. So let's not insist on this little technical comment. It's pretty trivial. So what we deduce is that for I beginner, xi over ai is clearly projective, never mind where the ample sheaves lie. And on the other hand, ai being an algebra of finite type over k and not 0, of course, if it contains k, we can find a homomorphism of ai into a field. In fact, we take a maximal ideal in ai, and we look at the homomorphism from ai into the quotient modulo the maximal ideal. We know that this is a finite field extension of k. That's Hilbert's Nullstellensatz. And if we make the ring extension from ai to k prime, we get, of course, the scheme xk prime deduced from x by making the base change from k to k prime. So we see that after making a finite base extension, x becomes crazy projective. But now we know that it descends because here it's finite and flat. We know that if we have descent data on a scheme, crazy projective scheme over such an extension, then they're effective and the thing that is descended is crazy projective. Now this argument which I have given here is of a rather general type. You see, it can be stated as a principle of the finite extension. If something which we would like to be true over k, but we don't know yet, becomes true after passing to an extension field, then for most properties that one might be interested in, it will be true that we will be able to prove that it will be true already after passing to a finite extension. Because the properties we have in mind will be properties that pass to the limit. So it is true after passing to k prime. It's true after passing to an algebra of finite type containing k prime. And therefore, by specializing speaking of properties that are stable by base extension, will be true after passing to a finite field extension. And sometimes we can descend to a finite field extension to k. So this is kind of a handy argument that is often useful. For instance, let's give another example. If x and y are two schemes that are finite presentation over k, if they become isomorphic over some extension field, they became already isomorphic. They were already isomorphic before. Or if you have an epimorphism from x to y, let's say a surjective morphism from x to y, after passing to an extension field, then we had already one after passing to a finite extension field, etc. You can multiply this kind of, if there's a group structure on x over k after passing to an extension field, there will be one group structure already after passing to a finite extension. So it's a very general type of argument. Now, I want to give an important case of where descent data can be made very concrete. Assume that we have a scheme S prime over S, never mind with its flat for the time being. We're not concerned with effectivity for the time being. And assume that a group object G over S, group scheme if you want, yeah. Alright, we are in a category of schemes, be a good group scheme. G over S operates on S prime. To the right if you want, never mind. Try as you wish. Operation like this. And assume that this operation turns S prime into what we call absolute torsor. Assume that the operation of G on S prime is simply transitive. I recall that this means that the map from S prime times G into S times S prime, which maps X comma G into X comma XG, that this is an isomorphism. All right. So S prime times S prime, the fiber product, which comes in defining descent data, can be interpreted as S prime times G, and the two arrows here can be interpreted as being the first projection PR1 and then the composition law pi. All right, and therefore, if we have a scheme X prime over S prime, let's say, the argument would work for any fiber category in fact, but let's take relative objects here, then it's two inverse images over S prime times G. How should I say this? Well, its first inverse image, let's say, by PR1 can be written as being X prime times G. Isn't it? That's just the first projection. We take the inverse image by the first projection. So that's just the product X prime times G, which is mapped to S prime times G by taking all this F prime here, by taking F prime times the identity in G. And here we take the first projection. And to say that we have Lewin data on X prime just means that we give another arrow here from this inverse image to X prime, which lies over the arrow pi, and which makes this second square Cartesian. Now call this here, what do I know? Pi lower x, if you want. This here was pi lower S prime. Now to give a morphism of X prime times G into X prime, that's the kind of thing we need in order to have G operate on the right on X prime. It's, if you want, an operation of G on X prime on the right, except that we still have to write associativity condition. Now, it's easy to check. That's purely no nonsense checking, in fact. It works in any category when we have such a situation. The gluing datum is a descent data if and only if, indeed, this operation in quotes of G on X prime is an actual operation, is associative. So in other words, to give descent data on X prime relative to S prime over S, when S prime is a pseudo-torsor on a grouped object G over S, is the same thing as to have G operate on X prime in such a way that the projection of X prime to S prime should be compatible with the operations of G, which expresses the commutativity, of course, of the second square here. So, descent data are just operations of the group here G. Assume, for instance, that the group G, it's quite an important case, is a constant group with value, let's say, pi now, gamma, let's say. Assume that we have just the usual group gamma, set-theoretic group gamma, and that G is just a constant group with value gamma over S. Then to give an operation of G on an object S prime over S is the same thing as to have the abstract say group gamma operate on S prime by automorphisms. And in the same way, to let gamma operate on X prime, to let G operate on X prime is the same thing as to have the set-theoretic group gamma operate on X prime by automorphisms on the right. And the compatibility just means that this projection is compatible, that the operation of gamma on both X prime and S prime commutes to this projection. So descent data in this case are just actions of gamma, which you know is something like a Galler group of S prime over S on X prime compatible to the action on S prime. All right. Now let's come back to this specific situation. Or well, why not remain abstract a minute more? And let's assume that in the category we are working in, that S prime goes to S is a morphism of one descent for relative objects. So here in schemes it would be for relative schemes. Then what we have said, I mean, the definition of one descent plus the remark I just made means that if for every x over s, we associate its inverse image on S prime, which is a fibered product, together with the operations of gamma on this inverse image, because if gamma operates on S prime, it operates on the fibered product of these two. Then we get in this way a fully faithful functor going from objects over S to objects over S prime endowed with operation of gamma compatible with the operations on S prime. Of course, I don't say that this fully faithful functor is an equivalence. I don't, because this would mean that we know how to solve the problem of whether descent data on x prime over s prime are effective. That's another problem. For instance, if we assume now that our morphism G from S prime to S is fully faithful and quasi-compact, we are now in the category of schemes. We know that this is a morphism of one descent. Then in fact our pseudo-torsor, we like to call it a torsor, because it will become trivialized after a base extension, namely S prime itself, which comes out to be kind of covering. You see it's faithfully flat, quasi-compact. Never mind. Then we know that G is of one descent for our relative schemes, and therefore a scheme X over S can be completely reconstructed when we know its inverse image on S prime endowed with the extra structure of the operation of either G in the general case or gamma in the special case of gamma on X prime. Okay.
The Rickow conditions appear as transitivity. The Rickow conditions for effective descent would in this case appear as transitivity of the operation.
Yes, that's it. Yeah, and that's, I mean, a formal verification. It has nothing to do with schemes really. It's general nonsense in categories. Even the fact that you have a pseudo-torsor in a way is not essential. Whenever you have a group object operating on an object S prime, you see, then you can construct the nerve of this operation, which is a simplicial object, which begins with, as I said, with S prime times